Shall we?
Okay, hello everyone. Welcome to EGRAPHS Workshop 2026. Thanks for coming.
I think we should just go ahead and get started with the program. Speakers, quick note, your time slot is your time slot. You may use as much of that as you would like for questions, but I will kick you off sharply because we have a full program. So without further ado, Cheng, please take it away.
Hi, so I'm Cheng Zhang from Worcester Polytech Institute, and today I'm going to talk about our collaborative work with Sam Coward, Philip Zapker, which is in the audience, and Alexandra Silva on incorporating fixed point equation into eGraph. So I first have a little bit of disclaimer. This work is very much a work in progress. I found a counterexample last Friday night, and I cried myself to sleep. And everything you see is frantically edited today at 4 a.m. And I need another sip of coffee. Things on the slide are probably incorrect and inelegant, but I hope I can convey an intuition of why this should work, and yell at me if you see anything obviously stupid. We might acknowledge you in our paper if you do. So I'm going to make everyone happy to say eGraphs are great. And now I'm going to make everyone sad by adding a quantifier to say they are great for algebraic theories. And for example, this is a very typical example used in EG. And you will see a lot of eGraph operations works very well for these because they correspond to algebraic theories where axioms are user-provided equality, substitution are defined by E-matching, congruence are by rebuilding, and equivalence closure are done by E-classes. So everything is great, everything is nice, but then we remember we are computer scientists, so we care about programs. For example, we want to sometimes reason about control flow. In here, we have an if statement where one branch executes a function, the other branch recurs, and a if statement where the first branch executes the function and the second branch recurs. And we sometimes also want to reason about data flows. In here, it's an SSA form, and we can turn this SSA form into streams. And these streams are also recursively defined. For example, if J starts with the initial assignment of 1, and if the first element of k is less than 10, i.e. the while loop, and then if the first element of j is less than 2, we execute the first condition, otherwise we execute the second condition. So these are programs that are not very native within eGraph. And what is missing within eGraph is that programs are really fixed point equations, right? Recursive program can be specified as fixed point equations, and they actually admit more equalities that are beyond the standard algebraic equalities. Specifically, fixed point equations have solutions. And if the solution coincide, we should be able to merge these E-class as well, and that corresponds to bisimulation. That is something I want to convince you for this talk. So let's look at a concrete example of how this solution coincidence work. This is the control flow example we have seen before. And we know that if B then S else R is equal to if not B then R else S, right? We are basically switching the branch of the if statement, and they should be the same. And we can rewrite via this rewrite rules, and we get a new fixed point equation. And we notice in this fixed point equations, P and Q are actually defined in exactly the same way. Therefore, we can conclude P equals to Q, right? So this is basically the intuition behind this. We have fixed point eGraph where the equality are split into two. One of them is recursive definitions, where you define your program, you define your variable, you define your data flow. And then we have rewrite on these recursive definitions, right? And these rewrites allows us to manipulate the fixed point equation to try to exhibit equalities. And the operations on these are inserting definitions, saturate by rewrites, and also saturate by simulation. And clearly, saturate by simulation is the most interesting part, and I will try to demonstrate how this operation works. So for here, we have the recursive definition. First, we insert the first recursive definition into the EGRAPH. And one of the things you notice is that in the first recursive definition, it says P equals to this huge if-then-else statement. And yet, the if-then-else statement and P are not within the same E-class. This is the mistake I made on Friday night and cost me a lot of pain. So we want to keep recursive definition opaque in the EGRAPH. And similarly, we can insert the recursive definition of Q. And because we have this rewrite rules, we can saturate via this rewrite rule. Specifically, in here, we notice that there's a pattern that matches the rewrite rule. Therefore, we are gonna insert another node to the back to the left side of the right side of the rewrite. Okay. And this is a very important point, is that variable unfolding are opaque with respect to the EGRAPH, in that sense that variable unfolding are not handled by the EGRAPH, only the rewrite are. So how do we handle variable unfolding? This is via transition systems. So given an EGRAPH, we can turn it into a transition system. In order to do this, I first marked all my E-classes. You can think of them as like E-class ID on top of it. And there are two ways to generate transitions. First one is stripping function symbols. So for example, if we start with the definition of P, which is the P-def E-class, we can strip the function symbol if then else, and we will get the E-class X, F, and P, right? That is simple enough. You are basically reversing the arrow on the EGRAPH. And another way to generate transition systems is by unfolding definitions. In here, for example, we notice that P is a variable E-class in the sense that it contains a variable P in there. We can unfold it into its definition, which is the P-def E-class. However, we mark this with a little colon equal sign to indicate that this is lifted by unfolding a definition. Okay. And in the same way, we can have the E-class for the definition of Q. We can lift it to have these kind of variable unfolding. And then we have the E-class for another way to define the definition of Q, which involves negation. And finally, we can also unfold the variable E-class Q there by linking it back into the definition of Q. In particular, we notice that these two looks very similar, right? If we replace P-def with Q-def, which are just a E-class, these two looks exactly the same. And this is where the bisimulation comes in. When we give these two the E-class that looks similar, we can construct a bisimulation on top of it. And if you read really hard into this definition, into the definition of bisimulation, it kind of extracts a fixed point equation. So this fixed point equation is if x equals to 0, then execute function, else recurse. This is exactly the fixed point equation we exhibit in the beginning to demonstrate that P and Q are supposed to be the same. And bisimulation exactly is doing that. So intuitively, bisimulation are extracting a fixed point equation that unifies the solution of two E-classes. And therefore, we can saturate by bisimulation because the equality is valid. And finally, we get this EGRAPH where the definition of P and Q are saturated. And because when we merge definition E-class, it's also good to merge their variable as well. So P and Q are also saturated together. And therefore, fixed point equation and E-graph lives happily ever after. Right? This turns out to be incredibly hard. So first challenge, it's sound rewrite versus sound re-equalities. So here it's a recursive definition where x is equals to 1 cons of x and y equals to 1 cons of tail of y. If you write this in Haskell, it will actually give you x. It's an infinite stream of ones. And y will have 1 as the first element. And if you try to get the second element or the third element and so on, you will run into infinite loops. Right? So in here, we can see that the semantics of x and it doesn't equal to the semantics of y. But let's consider the rewrite rule. X equals to tail of x. This indeed is a sound equality because if we take the tail of x, it's also an infinite stream of 1, and that is indeed equal to the semantics of x. However, it's not a sound rewrite because we can rewrite the fixed point equation into the fixed point equation on the bottom, and by simulation we can conclude x equals to y, and that is unsound, right? So the solution, we introduce a special kind of equalities that we hope approximates the sound rewrite while being intuitive to programmers, which are called variable generic equalities. Basically, these are the equalities that doesn't peek into the semantics of the variable. So formally, it means assigning variable to this equality should hold regardless of what you assign to the variable. For example, x plus y equals to y plus x. It's variable generic, but x equals to tail of x. It's not, because the second one relies on x being a constant stream. Right? And one of the nice things about variable generic equalities is that they are close under congruence, and that means if you start with a variable generic equality, E-matching on the variable generic equality will also generate a variable generic equality. So this means that E-matching works very well in this regard. Another challenge is unproductive cycle. This is one of the things we mentioned to like Ross and Max when we were talking, and this turns out to be a huge problem for both of us. Consider the following two rewrite rules. 2 is equal to identity function applied to 2. 3 equals to identity function applied to 3. Great, brilliant rewrite rules, very useful. And we can make this E-graph where like 2 is in it's unioned with identity of 2, 3 is unioned with identity of 3, right? And we have 2 E-classes, we name them 2 and 3. And if we turn them into transition systems, they look very similar. We can have a bisimulation on top of it, right? And this would unify 2 and 3, which I hope everyone here realizes is unsound. Last time I checked, 2 does not equal to 3. So what is the problem here? Intuitively, bisimulation are supposed to pick out a fixed point equation. And this is kind of the fixed point equation it picks out. It's a variable equals to the identity, defined as the identity of its variable. If you put this in Haskell, for example, you will get an infinite loops when you call the variable. So this does have a unique, this does have a solution, but it's not unique. For example, 2, if you plug in here, it will also balance the equation, and 3, if you plug in here, it will also balance the equation. So really, this is the confusion between rewrite and definition. So I hope this example shows you that rewrite and definition are very different objects. And box, defined as ID of box, is not the same as box equal to ID of box. So this is very, very subtle. And the solution, from the name you probably have guessed, we have some sort of productivity tracking. So all cycles need to be guarded by a productive result. That is one of these transitions marked by colon equal. If we recall our previous example, in here the cycle is going from pdef back into itself and qdef back into itself. But notice, in order to go back to itself, it needs to unfold the definition one time. And that, we hope, will make it sound. And I hope I cannot find any more counterexamples. The third challenge is non-unique solution. So we have a little taste of this. Specifically, formally, why is bisimulation sound? So previously, the explanation is, well, we restrict our semantic domain to a very small subset of programs. That is, all the fixed point equation within these has to have unique solutions. And we remember that rewrites need to preserve the solutions. And finally, it basically says all the recursive definition, if you want to merge them, they have to have unique solutions. And when do things have unique solutions? For people that are familiar with ROC or AGDA, they might know like co-inductive data types. And turns out in co-inductive data, when you want to work with co-inductive data types, this is one of the things you need to make sure of, that it's all the function you define need to have a unique solution, and they have a guardedness checker to guarantee that. And the last time I checked, programmer really enjoy writing program with guardedness checker. And indeed, most of the example we've seen so far failed the uniqueness check, right? So uniqueness to us feels like a very strong restrictions, and we are trying to remove this restriction. So original solution, we were trying to do pain and suffering with techniques from iteration theory, which is a theory that axiomatizes the canonical solution of a fixed point equations. And after I have encountered a counterexample on Friday night, I have a new solution. Pray that Alexandra will figure everything out. Okay, I think that's all I want to talk about. I hope you find this hard and depressing, and share my suffering.
Thank you so much, Cheng. We have about 6 minutes for questions. I'm happy to bring the mic to you. Phil, if you want to go ahead and start making moves to set up, that'd be great. Who's going to go first?
Hey.
So I must ask, what is the counterexample?
Oh, the counterexample is when you, that is a bit, so when you do merging, sometimes you cut the productive cycle in half, and you only have the first half of the productive cycle, and that half can be an identity function, for example, right? And then you have ensemble equalities. And that is a problem of merging variable E-class and definition E-class, because if you think of the transition coming out of it, you don't really know whether it's coming out of a variable or a definition, right? So you cannot keep track of productivity very effectively.
So maybe too obvious a question to ask, but plausibly you'd want to apply this to reason about control flow?
Yes.
So do you want to vamp a little bit on how useful this would be for reason about control flow in imperative programs?
Yes, that is a very good question. So if you know me, I did a little work called control flow GCAT a couple years ago, and it turns out to be really fast and effective, but the problem is you can only reason about control flow, right? So after every condition, it has to execute the same command. And that is very restrictive, because sometimes we want to take into account of some data flow properties, like, for example, if two commands that doesn't interact with each other, we should be able to switch them, right? This is somewhat aligned with the idea used in, for example, stream fusioning, right? And so this is one of the approach I'm trying to do, is incorporating this control flow idea with some little bit of data flow that are axiomatized as like input equations. Yeah.
great talk. So Eli Rosenthal implemented a partition refinement algorithm in EGLOG. I found it very similar. And what we learned from that TOEIC implementation is it seems there's duality between rebuilding and partition refinement, and maybe even unification. Have you thought about this?
Can you say the connection between what and partition refinement?
Rebuilding, like
Oh,
the congruence
rebuilding,
closure.
yes. So by simulation, it's closed under congruence. So if you have found a by simulation, you don't need to do rebuild under the by simulation. But the way we do by simulation is by checking every pair. That means like checking every pair and all the transition below it. That means that you still need to rebuild on top of it, right? So there are some efficiency to be saved if you want to save the, yeah.
Hi, Cheng.
Hi.
I wondered when you showed the example with 2 and 3 with the ID, that it would be unsound to conclude that 2 equals 3.
Yeah.
But in Haskell, if you view those as 2 different definitions of 2 and 3, then it would be sound to conclude that they are equal.
So
Can
that
you
is, sorry.
Can you say something about
Yes.
that?
So that is the thing. That is the difference between definition and rewrite, right? Rewrite doesn't need to admit a canonical solution, but definition need to. In Haskell, for example, it's a least solution, right? So this is why we need iteration theory to specify what canonical solution actually satisfy. Yep.
Okay, let's thank the speaker one more time.
Sorry.
Thank you. Whew.
Okay, Phil, take it away whenever you're
Those
ready.
slides up there. Oof. I was worried. Okay, I'm Philip Zucker, and I am like super pumped to be talking about lifting eGraphs today. Okay, this is what this is a variation of an eGraph that supports a particular notion of a rigid alpha canonical variables in the eGraph. And the aspect of this that I find particularly exciting is I think what I'm presenting is actually very, very simple and also very semantically driven. I'm like a very semantic kind of guy. I don't love term stuff. I want things like mean mathematical objects. So the plan today is I'm going to talk about well, first, things that are issues with name variables, a semantics for variables that I happen to like. Maybe you like a different semantics, but this is my time, so I'm going to talk about the one I like. Then how you can encode that in a simple nameless representation, and then we can improve that encoding using the concepts of lifting functions and thinnings, taking functions and making them take in more arguments, that some of which you throw away. That's what lifting is. And then finally, how to actually really bake this all into the eGraph in an eGraph modulo theory style, making a lifting eGraph. And there's 2 components to that, basically. Lift pulling smart constructors and a special little variation of the union find, the thinning union find, and then a brief comments about e-matching. OK, so in the beginning, there was sin. There was sin in the eGraph. OK? And from the beginning, the eGraph has been talking about variables. We've been talking about programs. We want to optimize programs. And a program that doesn't have any inputs actually isn't that interesting. So the original sin is an expression like this, sine of x. And it's not the sign that I'm like queasy about. It's the x. Like, what is x? I'm a crazy person or whatever, but like, and people don't share that disquiet, but I felt this disquiet from the get-go. OK? And so that's an explicit named representation. You have like a name x. And there's problems with explicit names. One problem is that there's a runaway generation of names during equality saturation, during generative processes. Sometimes you need fresh variables. And if you just have a gen sim and you just like make a new fresh variable, for example, this rewrite rule, if you have a proposition p and you rewrite it to for all x, p is true, but x is fresh, that's fine. But if you use a gen sim for that, you're going to fill your eGraph with a bunch of basically the same things, but like it's a bunch of junk. And you can try and play some tricks to try and like make that better. But it's leaked in elegance already. Second is scope hygiene. X times 0 is equal to 0. This is like a boogeyman for like worrying about variables. There's an X, the equality in an E-graph is bidirectional. And there's an X on the left and not on the right. And if you take some naive approach to dealing with lambdas, if there's a 0 that appears inside the lambda, you're kind of talking about rewriting it to also have an X in there. And so that X is not necessarily bound to anything anymore. And it's like, is that OK? I think there's semantics where it is OK, but it's like queasy making at least. A third issue is not enough sharing. We could have a very deep term, f of g of h of x, and then f of g of h of y, and they'll share absolutely no memory. You're like interning them into totally different things. And maybe you kind of meant those to be the same thing, or maybe you actually needed them to be different for other reasons. It's like all kind of shadowy about whether that's actually the same thing or not. And then finally, the thing that's sort of the hardest to notice, but I think the most interesting, is there's actually too much sharing when you use explicit variables naively. OK, so we come to the question of what is sine of x? Silly question, I guess, but like I'm a silly guy. Obviously, sine of x is this. It's this, it's that curve, that comfortable, familiar curve. One-dimensional function from r to r. X goes to sine of x. But, OK, there are contexts. If you just talk about sine of x and you don't include this maps to notation that I suddenly put up there, you also might be talking about this. This is also sine of x. OK, but those are totally different pictures. They have completely different types. You can't even compare them for equality, or I'd be inclined to say you can't compare them for equality, because one's R2 to R and one's R to R. And the thing that differentiates them is I use this maps to notation. So that little extra piece up there, I need to even make sense of what sine of x is even supposed to mean in this particular semantics that I so happen to like. So from this example, we come up with the idea of let's break the ambiguity. I want to know which one I'm talking about when I talk about sine of x. So the design principle here is that the context x comma y maps to is not where the term is. It's like part of what the term is. I want terms to mean things, and you need that extra little bit in order for things to actually mean things in the semantics I like. OK, so, but like, what the heck is x comma y maps to? I've just made more problems by introducing that. So let's encode this into the more familiar place of like ordinary first order terms and ordinary E-graph. OK, and so this is a naive, well-dimensioned, nameless representation I'm describing here. There's almost nothing to it. And if you have this problem where you're like conflating two things, we'll just spray indices and everything, and now you can tell the difference between the two. So everything should be indexed on the dimension / context D. If you talk about 42, it's actually 42 sub D, the 42 in the three-dimensional context, sine sub D plus sub D. And then if you're already doing this numbering game where I know I'm talking about R3, you should just refer to the variable by index. And that's also familiar from math class. And I'll call that var D sub I, the variable I in the dimension / context D. OK, and all of this is usable in ordinary E-graph. These are all ordinary E-nodes. Those D and I are like U64 fields in an ordinary E-node. OK, and then if we do that, this is what the example looks like. Now this is sine of 1, var 1, 0. And this is sine sub 2, var 2, 0. They're completely different syntactically. They don't hash cons into the same thing anymore. We've broken the ambiguity there. OK, and what's, again, emphasizing semantics, what's cool about this is that as a compositional pointwise functional semantics, so 42 sub D isn't just the number 42. It's a function that has D parameters and returns the constant 42. So it actually has type R to D to R. And the function 42 sub D is not the constant 42. They're like different things. And like conflating these two things was like, it is a perspective on what was causing all the confusion occurring with variables. And then this is really interesting. The variable, the var symbol, semantically, it's interpreted as a projection function. And I think if you're trying to come up with a semantic meaning of variables, a projection function is actually a very cool thing to be talking about. And this is kind of familiar from if you've seen like manifolds or something, where like x is just a scalar function on this shape, sphere or something. And like that's what it means. That's what x means. then, and this is sort of a little sleight of hand, sine sub d is not just the sine function, it's actually the pointwise application of the sine function. And the reason the reason it's like that, and it has this type, is we want to write ordinary looking expressions, kind of, sine of var. But var, we already said, is actually this functional object, is its meaning. So sine sub d actually has to take in a functional object as an argument. You could also talk about this as the partial application of the composition operation, if you prefer that. And then finally, there's plus, and this is actually the usual notion of adding functions. It's the pointwise addition of functions. So that's actually a very familiar thing. It's why functions are like a vector space, for example. Is this good? So the ambiguity is gone, and that's awesome. But now even more very similar entities share no memory. That was one of my complaints, right? Sine of 1 var 1 0 and sine of 2 var 0 var 2 0 share no memory. And I'm not complaining that it's not noticing inequality, because they aren't equal. They have completely different types. They should never be equal. But they're very, very clearly related entities. Like, why can I not share memory between these things? So there's a difference between equal and sharing memory. Those are like different things. OK, so if they're clearly related, in what sense are they related? What sense are those two semantic entities, those two plots, related? And one framework to talk about the relationship between them is the framework of lifting. And there are other frameworks. But so lift is quite simply you keep some arguments and you throw some away. You pass some of them along, but the other ones you dump on the floor. And also you keep them in order. And there's a one-line Python combinator that implements this. This is a thing you can write. It's a perfectly valid program. And it's parameterized by a thinning bit vector t, which has a 1 or true for the variable you want to keep, and a 0 or a false for the variables you want to throw away. And what this lets you do is it takes a function, for example, that takes 3 arguments, and I can turn it into a function that takes 7 arguments if I just throw away 4 of the arguments. That's what this thing is doing. And when I write this LaTeX notation, 1, 0, 1 means that I keep argument 0, I drop argument 1, and I keep argument 2. So that's what that means when you see that notation. And then if we apply that to our ongoing example, we can drop a lot of indices, and now it's sine of var is the one-dimensional object, the one-dimensional sine. And we can use the lifting that we want to pass along the 0th argument and drop the 2nd argument, and that gives us sine of x. If I want to talk about sine of y, it would be lift 0, 1. Okay? And all 3 of those share the same subterm in there. That can be interned into all the same stuff. And they only differ at the top by lifting. And then schematically, you can sort of see this is a schematic of like what's happening there. Like this thing is equal to that thing where you've thrown away one of the arguments. Okay, and then I want to take a hot beat to just like, publicize thinnings, because like that is the seed crystal from which this entire talk, this entire line of work like propagates out from. They're simple, they're actually simple, okay, and they're highly underappreciated, this concept. I did not invent thinnings. Thinnings are a thing that is associated with dependent type theory, but like actually has nothing to do with dependent type theory. It has as much to do with dependent type theory as the naturals have to do with dependent type theory. They are mathematical objects, they make sense. One lifts a function by thinning its argument list. Thinnings are strictly monotonic maps between totally ordered finite sets. If you're mathier, maybe that makes you happy. If you're not, maybe it doesn't. They're also a recipe to extract subsequences, and that's the sense that we're using them here. And I also like to think them as a compaction of multiple de Bruijn shifts. If you're used to using de Bruijn indices, you sometimes need to shift around indices in order to like bring a term into a new context. And if you keep doing that, you're going to like make all these gaps, and all those gaps can be described by a single thinning. So like a permutation is a compaction of many swaps, a thinning is a compaction of many de Bruijn shifts, is like an analogy I like. And they're in the same sort of mental space as permutations, but they're more minimalist. They're actually much simpler than permutations. They're just more unfamiliar. And that combination of like unfamiliarity, non-obvious, but actually like super simple, like makes my little antenna like go right up. And I'm like, people should be, not just in lifting EGRAPHS, people should be spraying these things all over the place. Like this is an awesome, thinnings are an awesome idea. Okay, and then they have a notion of identity and composition, which you can visualize. if I take a 2-argument function, lift it to a 3-argument function, then lift it to a 5-argument function in 2 stages, I can do that in a single stage by dumping away all the stuff that eventually get dumped. And there's like a 5-line Python function that will take in those 2 bit vectors and give out that bit vector. So this is all implementable. It's not just like crazy diagrams. It's like there's code behind all of this, simple code even. And then there are rules for lifting. There's a constant folding rule for 2 lifts, which I just described how you're going to compute that i.j. So that lets you like compact 2 lifts together. And then there's also interesting this polling/homomorphism rule, which lets you, and what this means semantically is if I take x and y and I give them redundant arguments and then pointwise apply f, that's the same thing as pointwise applying f and then giving the whole thing redundant arguments. That's what that equation is saying. But like structurally, it lets you push lifts inside of stuff and pull lifts outside of stuff, which is like a useful thing to be doing in lifting eGraphs. OK, so I'm into baking stuff in. Everything I described before this slide, it actually could be done in an ordinary eGraph, and maybe you prefer doing that. Make an ordinary lift enode, make those rules I just wrote, ordinary quality saturation rules. It has a model, it has semantics, like that's a way of dealing with variables. But I want to bake it in. And it's tempting because these are bit vectors, and bit vectors are like very, very small pieces of data. So this kind of fits well with this thing I talked about last year, eGraph modulo theories, and this idea of fat identifiers. The idea of everywhere, the recipe, the cookbook for eGraph modulo theories, everywhere you saw an integer identifier, replace it with a fat identifier. And in this case, the fat identifier is a tuple of the ordinary integer identifier and the thinning bit vector. Okay, and then we're just going to go through the pieces of the eGraph and see like what do we do when there's a fat identifier here instead of a regular identifier. So the first thing we have is an ordinary enode would have an IDs there, a list of children, IDs of the children, but now they're going to be fat IDs. Okay, and what you can do is if you've been given children that have been sort of redundantly lifted in the same way, you can pull out that common lifting up to the top, only intern in the sort of minimal context necessary. Okay, so this will achieve more sharing in the eGraph. You'll have to intern less things. And the commonality between the 2-dimensional sign and the 1-dimensional sign is because you'll just see that they're different lifted things of the same identifier. Interestingly, this is kind of looks like a free variable analysis, but it's better than a free variable analysis, I think, in the sense that it's semantically driven and also can't be out of date, actually. Like, you kind of have to worry about the free variable analysis is finishing to like make sure what you're doing is sound. But because like this is actually semantically meaningful, it's like always sound. It's just like always makes sense what you're doing. I saw quizzical looks at that, but I believe it. OK, some examples. Here is like the zero rarity function 42 lifted up to take 4 arguments. Pulling doesn't do anything to it. If then I added 2 of those together, naively you would get this expression. But there's a common lifting on the 2, so you can pull this out. And if I instead did this in a 2-variable context, if I actually interned this EID, this enode in the first column, you'd get a different thing. But because you can do the lift pulling smart constructor, you end up with the same common subterm. And those lifts are just lightweight annotations on the identifiers. And then here's a more complicated example, z plus 42, where z is the second variable. So this is the identity function that's been lifted up into a for context to turn it into a projection function, the constant function. And then the common thing you can lift out is actually 0, 1, 0, 1, 0. And note that you have to lift 42 to even make sense to be adding it to the identity function. The identity function takes in 1 argument, and 42 intrinsically takes 0 arguments. So you need a lifting to sort of mediate that to be sound and have things make type sense. The thinning union find. So the version of union finds that I kind of like is the arena style, where you have this giant vector or list. And when you want to traverse up the union find, you look at your entry in the list, and that has the identifier of your parent. And you can keep doing that. And there is this idea of a group union find, for which the offset union find is an example of that. And what you can have is fat identifiers, where the fat part of the identifier is a group element. And the offset union find in particular lets you support equations intrinsically that look like this. E8 minus 3 equals E3 plus 11. You assert that to the union find when you call a union. And then the union find orients it into this parent-child-parent relationship. And when I write something like that, what I mean is that at the 8th entry of the union find, there is an annotation 14 and a parent identifier 3. That's what this like LaTeX here notation actually means when you look at the data structure. And this all kind of works in the group union find. When you do find, you just need to compose the group elements as you traverse up the find chain. And the same thing works with the lifting union find. It actually doesn't change at all, that aspect of it. You just need to use composition of thinnings as you traverse up the chain. But union is a little bit different. So there's sort of a, here's kind of the algorithm, I guess. So the thing receives 2 fat EIDs. If they're commonly lifted, you can peel off the common liftings, like you peel off in unification 2 cons cells equal to each other. You can peel off the cons, and that's because cons is an injective function. Also, lift is semantically an injective function. Like it takes 2 different things to 2 different things when you apply lift. But that doesn't always peel off all the lifts. So the way you can deal with that is picking the parent is sometimes forced / requires make set in order to like make it work. So and the reason this is like different from the group union find is because lift sub t is not an invertible function semantically. It's going between differently sized domains and like it's just not an invertible function. So it's a slight twist. It seems that having the group character is sufficient but not necessary, in my opinion, for something that feels still like a union find. 5, okay. And then the semantics, when you actually union 2 things that have different thinnings on them, what you're actually learning is that a direction you thought maybe wasn't constant actually is constant. So that's the semantic meaning of equating 2 different thinnings on an EID. And so here's the typical example of what this looks like. If I said y times 1 is equal to y in the 2 context, the pulled form of it looks like that. And then if we intern those inner expressions and I say they become ID 17 and I42, the lifts stay out there, and then this is what the thinning union find receives. These are 2 fat EIDs as the 2 arguments to union. Then we note that it's the same thinning on top of them. We can peel that off. Now inside the implementation of union, we know that they're the same, and we can pick either direction just like we ordinarily would in a union find. But this boogeyman example, I talked about x times 0 equals 0 at the beginning, redundancies, redundant use of variables. This is the sort of max pulled form of this. When you intern those 2 sides, you end up with a lift over here and no lift over here, okay? And I mean, actually, it's kind of obvious through this example, like what you can make work is, well, it's just the right-hand side has to be the one that ends up being the parent. Then I don't have to solve for anything. Yeah. And then E-matching. Okay, so the typical case of E-matching is not that complicated to actually like operationally what you're going to do. As you're like traversing down your E-nodes, as you're like going down your E-nodes during E-matching, you're just accumulating the thinnings that appear, you're composing the thinnings that appear on the children EIDs of the E-nodes, and you just compose them as they go down, and they end up being fat EIDs in the substitution that's returned to you. And the way that's justified inside of like the term rewriting model of this thing is that E-matching is actually pushing lifts down during the process. So we know that this is a true equality of liftings, and you are matching on something that's lifted in some way on an E, and then you replace E with the E node, one of the E nodes that's in that E class, and now you have lift of F of E, some E1, E2, and then to like kind of put it back into the spot where you can recur, you need to push that outer lift inside of the arguments. Redundancies are a bit trickier to deal with. So these are like equations that are living inside of the union find. And the first easy thing to do is just like, don't worry about it. Don't match through those. And the reason I think that's actually kind of a good strategy is because if you deal with this problem, you're matching into expressions that use variables redundantly, which is like not a good place to be looking, probably. Like you probably aren't interested in stuff that's like has a bunch of variables that ultimately don't matter because you multiply them by 0 or something. But if you want to, you can do it. And what you need to do is solve this lifting equation where This is the EID you're matching against, and this lift sub k is coming from the union find. And then there's multiple solutions of how you might find such a j to solve that equation. And in the named form, what this corresponds to is if you had matching 0 against a times 0 in the 2 context, there should be 2 solutions, x and y. So that's where that extra bit is coming from. Related work, slotted EGRAPHS. To some degree, this work is a combination of slotted EGRAPHS and Connor McBride's. Everybody's got to be somewhere. Her comments on thinnings on Mastodon was like the initiation for this work. And also Rudy Schneider like really talked to me a lot and really helped me understand slotted EGRAPHS. And this is like basically the same bones as slotted EGRAPHS, just like putting in something else instead of permutations, kind of. Also, semantics of type judgments. The semantics I described is basically the semantics of type judgments, where if you had placed everywhere I'd said maps to with a turnstile, I think we're kind of talking about the same thing. But turnstile feels fancy and maps to feels nice and simple. Explicit weakening calculi. Weakening is another word maybe you might use for thinning or lifting. There is such thing as explicit weakening ones. And De Bruyne suck floating from Pavel's blog post, Binders and EGRAPHS. And Oleg Kaselyov's Landinski semantically. Here's a way of visualizing it. There's a blog post. I'm going to put up a preprint. You can visualize it by fattening every single edge in the eGraph to have thinnings on it. That's like what you do. I don't know that actually helps me think about it that much, but like people love pictures, so this does make sense. X times y equals y times x corresponds to that picture. All right, that's what I got. I'm probably out of time.
Thanks, Phil. I think we have time for one quick question as we switch over to the next talk.
So why is thinning enough? Because permutation is usually like the standard way to deal with this. Do you have any intuition why thinning is enough?
It's not enough. I think permutations is giving you more, but then you have to implement more. And I think this is actually like a simpler, like slotted eGraphs already gave you permutations. And this is asking for less, but it's a much simpler thing to talk about its semantics and how to do it. There's a middle ground between slotted. Rudy and I think there's a middle ground between the two where you put a total order on all of your slots. And so, but I'm still a little hazy on like how that middle ground works.
Okay. Thanks again, Phil. I'm sure Phil would be excited to chat about this work offline with any of you who didn't get your questions in. And now we will transition to a remote talk on predicate eGraphs. Is the remote talk ready, queued up? Okay.
Hello? Hi there, can you hear me?
I can hear you. I don't know if you can hear me.
I can hear you, excellent. Are we ready?
Can you please reshare your screen?
Ah. There we go.
Can you change the scene back? Okay, we can see you, but we cannot see your screen just yet.
Okay, it looks good here.
efficient way to very efficient way to build an EGRAPH, but then backtrack to a previous version as efficiently as possible. We wanted the thing to be very high performance, so we use lots of arena allocation, and then we use integers as pointers into these arenas, but then you're on your own because you can't rely on Rust to tell you you're doing the right things with pointers. So we started using Varus to verify parts of the mechanics of the EGRAPH. And then we wanted to solve AC explosion. So as you know, when you use eglog, you often have to express associativity and commutativity using rewrite rules, and here we use canonization to implement the same as replacement for rules. And we also wanted batch proof extraction for all equivalent nodes, and we came up with a shadow data structure like union find and very efficient least common ancestor algorithm. And so the semi-persistent and AC matching, like canonized AC matching, already exists in a SMT solver called AltErgo since 2008. So nothing I'm presenting here is new. The only new thing is like it's written in Rust and verified using Varus. Yeah, and also we just recently open sourced the code, so everyone's welcome now to use it or contribute. So semi-persistence, I'm going to start with that. That's the foundational layer. You know, like functional data structures, you have fully persistent vectors or arrays where every time you modify the array, you keep track of a negative diff with respect to the previous version. And you end up with this forest of diff, and then you can restore any previous version, and you can also jump back to any later version as you want. The semi-persistence actually drops half of that capacity. You can just backtrack to your previous version, but what you gain is optimum read and write access to the current version of the most recent version of the array. And what you like to do this, you just keep the current live version of the array at the bottom here, so with different values at different indices. And every time you do a modification, you basically store a negative diff of what that value was when you did the modification, and you manage these different versions as a stack. So you have this mark and restore protocol where every time you mark a version of the current version of the array, you're going to capture the first modification you do post mark, and then you're going to ignore later modifications, and then at any point in time you can reverse to one of the previous versions, and you pop all the diff stack. So you get at most one diff entry per layer of the stack, so you have a guarantee of how big the diff could grow. You're never going to have a diff that grows too big. And you can always restore a previous version in a backtracking fashion. So this is an example of the lifetime of such a vector. So you can start the branch 0, you can start with the current version 0, 0. Then you can take a first mark of that branch, a second mark, a third mark, and then you can decide you want to backtrack to mark 1, and then you open a new branch in the history of the data structure. You can continue and then backtrack to an earlier version on the 0 branch, and start branching again. So which means semi-persistence supports backtracking, but very efficiently. And we have this discipline of like checking branch counter and depth along the branch to prevent you from trying to restore to an invalidated snapshot. So we have guarantees about not ever crashing, basically, and always being able to restore. So from this single primitive, we were able to build hash maps using open addressing, sparse sets, arena allocated linked lists, circular lists, and all the way up to a fully fleshed out union find, node caches, symbol registry, so everything you need to build an EGRAPH. And now with this semi-persistent discipline, we have an EGRAPH data structure that you can tag different versions along a branch. It starts recording diffs, and at any point in time, you can backtrack to your previous version by catapulting the negative diffs back into the EGRAPH, and you restore the current state, the previous state. And you have a capped size and very efficient diff encoding. And So this lets us now use EGRAPHS inside of backtracking algorithms very easily, and the memory consumption is kept under tight control. And to make sure everything works as we expect, we started proving all these foundational layers using Varus. So for each of the data structures, we have a math abstraction and well-formedness predicates that were proved with Varus. And the key properties of that backtracking mechanism is that when you activate diff tracking, the whole data structure basically behaves as a stack of deep copies, but it only stores sparse diffs. And since we have Varus also verification, we were able to very aggressively optimize the encodings without having any fear for bugs. But so that's how we achieved backtracking. So the second feature of that eGraph is that we offer native support for associativity and commutativity, and also idempotence properties. So we spent a lot of time making sure the surface syntax for that feature was ergonomic. So what you can do now is declare algebraic properties for your functions. AC are going to be represented as canonized multisets. ACI are going to be sets, and associative are going to be sequences. And you also have binary commutative operations where the canonization is just ordering of the operands. But so you realize, like, syntactically, when you start working with this, you need to introduce in the syntax rest variables. So you can say I want to rewrite an OR applied to a not of a not X, but then there's going to be a trail of like other elements in that multiset under the OR. And then you need to be able to reference those variables in the right-hand sides of rules as well. So these variables are typed either multiset or set or sequence. So which means to make it ergonomic to express rules, you have to have that syntax that has basically rest variables and comprehensions. So the comprehension syntax on the right-hand side kind of looks like Python. You can say I want to match mul of A over add of X with multiplicity K, because that's a multiset term. And I'm going to have some rest multiset. And you want to map a constructor over that multiset on the right-hand side. So we have this comprehension syntax that lets you build new terms, and the double dot is the splicing, which lets you inline the transform rest variable into like a new term. So we have set comprehension syntax for ACI operations. We have multiset for AC operators, and we have sequence comprehensions for A operators. And every time we build a new term like this, it has to be recanonized on the fly. So flattened, canonized, sorted, everything happens implicitly every time you build terms. So yeah, so this also means that from an implementation perspective, we have really different kinds of nodes, unlike EGLOG or other eGraphs where everything's homogeneous in terms of representation. We have actually different types and different representations and different invariants for every type of algebraic property. So yeah, as I said, sorted pairs for C, flattened sequences with order preserved for A, sorted multisets and sets, dedupt, unique. And canonization also involves like representing everything using class representative at that point in time. So this interacts also with performance. So we use like arena allocations everywhere, arena allocators, which means our node caches are partitioned, and in each cache of nodes of any given type, we have like a dense indexing of the nodes. Like they all have like a dense identifier in 0n. But then we also have this global namespace where all the nodes live, so we handle that union ourselves. So we have a routing table that assigns global identifiers to nodes, but that routing table tells us global node I is actually local node J in some node cache that has that special representation. And we have this double, like this two-step ID allocation. But what we get is like a super cache-friendly way of representing nodes. of different types, but we don't have this homogeneous tabular representation that eglog has. So now I'm going to zoom into how we represent variadic nodes. Nodes that can have different numbers of children nodes, like the AC and ACI nodes in A. So what we do for these nodes is an AC node that represents a multiset, essentially. We're going to have a header node that has a fixed structure, like an operation and a start and stop index within a contiguous pool. So all the children of all the AC nodes are concatenated into a single node pool. And then a given node is just a slice of that pool. And so this means that we have a super cache-friendly layout, and we have a homogeneous representation for all these AC nodes, even though they have variadic, children lists. But this also means that when you recanonize nodes in place, and you discover new equalities between children nodes, those slices can shrink. So you could be tempted to shuffle the things and keep everything compact. We just shrink the slice in place, and we just lose a little bit of storage. But we can basically maintain that representation. And that's homogeneous, and that's where we can do AC matching later. We can AC match on that stuff. All right, so now matching. So now we have these different sets of nodes with different representation invariants, and we want to have a homogeneous way of doing pattern matching on them, and including AC canonized matching. So to do this, we used the leapfrog approach that eglog introduced. And we basically, with every round of saturation, we build 4 indexes of nodes. So one of them is the by up index. So given an operator, give me all the nodes that have this operator as operator. And this is going to be a sorted index, so we can do leapfrog. So these are just lists of integers, basically. We have the by repr, which given an E-class, give me all the nodes that are in that E-class. And the by child in position, so given an E-class and a position, like operand position, give me all the nodes that have this E-class in position as parents. So parents at the shy slot, basically. So these are for the traditional nodes with fixed arity. And for nodes that are variadic, we just index them via one of the child they can contain. So we have this index that goes from an E-class identifier to all the variadic nodes parents that have that child somewhere in their child list. So we can index into AC and ACI nodes like this using a single index. So now when you want to match a pattern like f of g of x and h of x, that's the case without AC nodes, just as a baseline. So the first thing we do is we decompose that pattern into atomic patterns. We introduce intermediate e-node variables. So u is going to be g of x, v is going to be h of x, root is going to be f of uv. And basically that set of atomic patterns gets compiled into that procedure where you're going to iterate over the index. So for u in all nodes that have g as operand, as operator, let x be the child of u at position 0. And then you have a leapfrog stage where you're going to be for every v in the intersection of the nodes that have h as operator and have x at position 0. And then for all the root nodes in the intersection of these twin indices, so operators that start with f, have u at position 0 and have v at position 1. So that's a 3-way leapfrog. Then you can emit a full binding. So every shared variables between those atomic patterns becomes a joint key. That's the standard eglog's thing. So in practice, it's not a loop like that. It's every pattern gets compiled into a sequence of instructions that gets executed by a VM. But when you want to introduce AC decomposition in that picture, all it takes is add a new type of loop that enumerates multiset matches, basically. So now if we have f of a applied to add of x k1, y k2 as a AC pattern and some rest variable, we decompose into atomic patterns as well. So n1 is going to be an AC node, with X and Y children, and then some rest that we treat as a multi-set variable. And the root pattern is going to be F and A and 1. So we start kind of the same. We start from the root, let's say. We match all these nodes. We bind A, we bind N1. So in that case, N1 is going to be forced to be a node that has the AC operation add. And then at this point, that's where we start stepping into the AC decomposition of the pattern. So we bind the residual to all the children of node N1. So that's a multiset. And then for every X in the residual, we're going to enumerate bindings of X and Y. So we start by binding X. We bind also the multiplicity of X to K1. And then we subtract XK1 from the residual. And then we do the same for Y in the residual that's been shrunk. We bind Y, we bind K2, and then we do multi-step subtraction again. The residual now is going to be a rest variable, and we can emit a full binding that way. Then we add Y back into the residual, add X back, like continue looping. So what this does basically is it enumerates all partitions of the multiset where you extract like X, one X and one Y, full cardinality, and just drop the rest of the multiset in the comprehension. So it's really like a very minor extension to leapfrog AC matching. And since our index like in two AC nodes is like just a single homogeneous index, it's actually pretty easy to do. So in practice, we don't really compile those patterns into eager loops. We compile them into like sequences of instructions for a virtual machine that's embedded in the runtime. And the mechanics of it is basically we have a stateful iterator that implements those nested loops. And we can pull matches one by one from the iterator lazily. So this also avoids like blowing up the memory by saturating the memory. Like if you're looking for a specific match, you can pull them one by one and filter on the fly. You're not going to allocate storage for all these intermediate matches. But anyway, so since we implement maximum partition semantics for the AC matches, we're insensitive to the actual multiplicity of the elements in the multiset, and we won't blow up. So we're not going to literally enumerate all the possible multisets, but just maximum partitions of the multiset. We can also add multiplicity constraints in the language. So you can say I want to match X, but only if multiplicity is superior or equal to some constant. And then when you have multiple uses of the same variable with different constraints, we integrate all these constraints into an interval, and we basically filter on the fly like the matches that don't satisfy that constraint. Yeah, so now proof logging. So the way we do proof logging is to introduce a second ghost union find that we never compress. We don't do path compression on this one, so it keeps the full trail. And every time there's a merge, we record the justification in that union find. And every time a node gets recanonized, we also store it in a side array of nodes so that we can start again from the actual root thing and have the full history. And so we are able to explain any pair of like A, B terms that land in the same equivalence class by just doing least common ancestor search in that proof forest. And we discovered a very efficient LCA algorithm. It's called the Bender-Farag-Colton algorithm from 2000. If you want to do batch extraction, you have a linear pass that pre-computes basically all possible least common ancestors, and then for any pair of terms, you have O1 extraction. So if you want to do batch proof logging, you can actually do that very efficiently. And all of that is also semi-persistent, so you can log proofs on the fly. All right. So in conclusion, there's not much there's not much novelty in that data implementation. All the IDs are pre-existing, but we try to implement them in a verified way. So we haven't yet verified the thing fully. So far, we've verified the lowest layers, the raw data structures, but we're working our way up to the actual eGraph invariants. And the next steps would be like I've seen a lot of very crazy extensions of eGraphs that I want to be able to use, but slotted eGraphs or thinnings or colored eGraphs and everything, all super interesting. But making sure you implement that right seems kind of tricky. So the goal with this was to put some formal verification scaffolding around an eGraph, trying to engineer it as well as possible, and basically have a place where people could come and experiment with new eGraphs algorithms, but also have that verification scaffolding around it. So that's why also we open source it to try to make this happen. So yeah, we hope that's going to be maybe a framework that people are going to consider when they want to implement tricky extensions of eGraphs. And yeah, that's going to be it for me. If you have any questions.
Thank you, Remy, for a great talk. We have time for a couple questions. One thing that I do want to emphasize is that you should go to that link. There's a lot of great code there and a lot of great also high-level documentation about the motivations and design decisions here.
Super fantastic. I was wondering if you could characterize differences on performance differences across workloads.
So I've compared the implementation to egglog, and in raw throughput and pattern matching, we have a 30% gain in terms of number of matches per second. But I need to confirm all of that because proving some parts of it have basically called for de-optimization, and now I'm trying to re-optimize everything. So we haven't yet conducted extensive benchmarking, but cool. Yeah.
Very exciting. Thanks so much.
Thanks for the talk. Does it get tricky if you have a lot of constraints on what is in the set? I can imagine if your multi-sets or sets get quite large, enumerating all the partitions will get very expensive. But in practice, and that might be the user's fault for posing such a problem, but it's also possible to pose problems where that wouldn't be an issue. It seems like it's hard to constrain the enumeration effectively. Yeah,
so we're already happy to contain the full explosion, but it still explodes, yeah. The bet we have is that we do this streaming operator where we can actually filter on the fly and then even avoid to materialize them in the memory of the computer, but you still have to go over them and ditch them. And containing that second thing of explosion and basically being able to hint at, well, I want to start leapfrogging in such a way or such other way to just avoid looking at some of the candidates and enumerate them in a specific order. I don't think we have a good solution for this, but leapfrog is cool because you can actually guide, you can select which atoms you start with, and so you could maybe avoid explosion this way, but I don't have a good answer.
Thanks.
Okay, and let's thank the speaker one more time. Okay, and moving on, Tariq will continue on this theme of the challenges of associativity and commutativity. So please take it away whenever you're ready.
Okay, mic check. Perfect. So I will basically continue where we left off, but we have a bunch of differences. I'm Tarek Rosin, and this was work done at Saarland University together with Marcel Ulrich and Sebastian Hack. So many of us view an eGraph like this as a visual, as a graph, but there are a bunch of different perspectives on the same data structure. Yeah, I inserted the term on the left into the eGraph, and if we now, for example, try to apply associativity to it, we would insert the new pattern match, the new expression, and unify it at the root to the existing one. And now the different perspectives would be, if we label the E-classes as well, we can write it as a term rewriting system, which rewrites to the E-class IDs. So the E-class IDs are essentially part of our original theory as just basically constants. And another perspective on the same data structure would be as relations, where this is the relation only for the multiplication operator. So we left out the inverse. And as you can see, it's essentially the same, just in a different notation. We will be using both of those variants interchangeably. And when I say an e-node, I mean either a tuple in the database or one of the rewrite rules in the term rewriting system. Okay, so how do we generally match patterns in an eGraph? We've seen this in the previous talk. We use query algorithms. This was prior work by Zhang. And essentially, when we have a pattern like this one, we lower it to a flattened representation, where we always insert like a E-class ID, a root element, to link the flattened atoms together. And then we have the leapfrog algorithm, or the generic join algorithm, which we already saw previously. In order to make it efficient in just traditional eGraphs, nothing with AC yet, we store the relations as tries. So we take all the tuples and we just insert them in the trie like this to share the prefixes. Then how the algorithm proceeds is, at each stage we compute all candidate values that the variable x can take. And we do this by looking at the current level, taking the intersection, and in this case the intersection is only the E-class ID A. So next up we would loop over all candidates and restrict our data structure to just the path where A was chosen. So A is fixed. Next up we would repeat this for all the variables. And there's a small trick we can do for the roots, or in general for the roots of an atom. We don't need to loop over all candidates because there's a functional dependency from, in this case, x and y towards the variable r. Intuitively speaking, if you know the e-node, multiply x by y, then you can look up the ID in the hash table we already use for hash consing. So you don't need to store this even in our relation, in our tries. We can reuse this interning or hash consing table to find the one value, the one unique value, and no e-node is contained in two different e-classes. We will be using this later. Okay. And then after we have considered our candidate, we need to walk up the trie again. So this gives us the trie cursor interface, where we have a few functions which are basically required to implement this traversal. The first and kind of most important one would be select, which in this case is just follow the edge you selected. Unselect is walking it back up, walking back up to the parent. Keys would be to get all different outgoing edges at the current node. And then contains and the size are mainly needed to implement the set intersection. Okay, moving on. In traditional eGraphs, we store our data like kind of like this. And in a multi-set eGraph, if we now want to bring AC into the picture, we can flatten it together like in the previous talk and have just one multi-set representation, one variadic representation for all the nodes that were in here. And this also allows us to have a canonical representation for an already AC-saturated eGraph. In here, this part of the eGraph is not even saturated yet, so it's leaving out a few E nodes. And the database representation would be this one. And notable, we only do this for the relations for the operators that have the AC property. The others we leave untouched. Okay, so what changes about pattern matching? We compile the pattern to kind of the same lowering, but we introduce a new formal variable. The purpose of this is to differentiate multisets, which we'll see in the next slide. If we want to implement the tricursor interface now for this kind of relation, we would instead, when selecting, remove the key from the multiset once. And when unselecting, we just put it back into the multiset. The keys are essentially the support of the multiset, so all the unique elements. And containment and approximate size are, again, self-explanatory. So what do we need this T for? Namely, if we look at the original algorithm, in order to use the tricursor interface as I just presented, we need to have only one multiset at a time, which we can index into. And we introduced this T to select which multiset we are using. So it's an outer for loop around the pattern match, which goes through the multisets one by one. And it's opaque to the users. They don't have to know about this. And the concrete values also don't matter. It's just to separate. Okay, with this, we would again take the same intersection, but this time remove A from the multiset. And the same goes for Y. But now we have a bit of a problem. Namely, in traditional EGRAPHS, every subterm is represented. Every subterm is contained in the EGRAPH. If we now try to look up the multiplication between A and E3 in the hash cons, there is no entry for it, so it has no E-class ID. And we don't want to allocate E-class IDs during matching, just freely. So what we do instead is we create ephemeral, so-called ephemeral E-class IDs. These exist from during matching until when we apply the pattern, so when we insert the other side of the pattern. Yes, and essentially they just have one bit flipped, and we have to store the E-node associated with each ephemeral E-node until we have figured out whether we want to keep this as a match or not. Okay, so this was about matching, but the equality saturation algorithm consists of a few parts, namely also congruence closure or rebuilding. And there is actually a very rich existing literature on algorithms. There's one by Kapoor, which we will be using, and it works as follows. So the first step is to mark you focus on a single relation at a time, and you mark all E-nodes in there as unprocessed or as dirty. Then you take a single one and you update it, you canonicalize it with a union find. Then you simplify this one E-node you selected with all the already processed E-nodes to maybe shrink it. Now comes the complicated part. You take your simplified E-node and you take you compute all critical pairs between the clean E-nodes you already have. We see in a second why this is necessary. Okay, and last but not least, we inter-reduce all the clean E-nodes with a new one we are adding to the set of clean E-nodes. And we repeat, we go back to step 2 if we still have dirty E-nodes left. So let's see an example of that. If this is our small set of E-nodes, we have to choose, we already marked them as dirty, so we now have to choose one arbitrarily. Let's just pick this one. There is no union find right now that modifies it. There's also no clean E-nodes which can simplify it. So there's also no clean E-nodes with which we can compute critical pairs, so we'll just add it over here. And let's repeat. Now let's pick this E-node. And here, there's nothing to canonicalize, there's nothing to simplify. To be precise, by simplify, I mean using the rewrite rule on the right to simplify the right-hand side of the rewrite rule over here. But it doesn't match, so now we have to compute the critical pairs. In this case, these two have a non-trivial overlap, namely A, and we can create the ground NGU like this, and then we have the property that it one time rewrites into E2 times E3, and one time it rewrites into E4 times D. These two are new E-nodes that were not present in the previous eGraph, and but they break the property that it canonicalizes. So we unify them by just adding a rewrite rule that makes these two equal. Okay, so we add these two rewrite rules with a newly added E5, and we are done with processing this one. All right. Okay, so I think you get the gist. Here are some results. The memory savings are, I would say, very significant because we don't store all the subterms. We get away with storing only, or oftentimes only, one canonical representation. So, for example, in this case where we multiply A 10 times by itself, it adds nothing. It's basically free. And one counterexample is up there. H is here supposed to be a homomorphism. Okay, so in some cases we save up on space asymptotically, and in many cases it's constant or linear in space. However, it's not all that great because at the same time the algorithm is not complete for pattern matching. Let me give you an example. Here we have AB and we have the A inverse pulled out, right? So if we apply pattern matching on this, we would find that A via E3 gets cancelled. However, if we were to first apply congruence closure, we would factor out the A times B, and now, because our algorithm scans over a single multiset, we are no longer able to see that A is in connection to the A inverse, because our algorithm doesn't iteratively unfold or something like that. And yeah. Okay. And then there's maybe the question whether, even if it doesn't work all the time, does it at least save memory all the time? And here the answer is also more nuanced, because the homomorphism case is an unfortunate counterexample. What happens here intuitively is that we wrap the H around every variable. And this causes all subterms to be materialized and be stored. So the advantage we get from storing only one representation or only one canonical representation is lost. And furthermore, we perform worse than traditional equality saturation in this case, because in egg or egglog, you store the nodes as binary. And with this, we also will have all the ternary variants and all the arity 4 and so on. Okay, so to conclude, there's a lot of future work to make this really, really efficient. And maybe a question is, when is it efficient? Or how much is the effect of completeness, or how devastating is the effect of the missing completeness? And can we extend this to other theories by implementing the tricursor interface? And last but not least, we have not talked about extraction. So depending on your cost function, extraction might be even the harder problem. Okay, credits to these two papers for implementing half of what I presented. And that's it.
Great, thank you for the great talk. We have plenty of time for
question. Does this always terminate? Does the AC congruence closure part always terminate?
Yes. So in the paper by Kapoor, he's using, I think, Dickinson's lemma to prove that the congruence closure algorithm does terminate. Any other questions?
I have a quick question. I mean, you mentioned that part of the reason why on some of these degenerate cases you perform worse than conventional equality saturation is this subterm materialization issue. One of the things that Phil mentioned in his talk is, he said intuitively certain of these, in his was a different setting with these redundant terms. He was talking about how these are not interesting or not likely to be interesting to many applications. I'm wondering, I'm sure you've thought about, in terms of future work, how do we make progress in this subterm materialization question, assuming that in most cases, many of them are probably not interesting. How do we make sense of that?
Okay, I would kind of disagree. I think there are cases where you have an interesting rule like a homomorphism, which is useful, so you need to think about it. One option is maybe to extend it to other theories. So maybe you have AC plus homomorphism, and you have a data structure for that. It's not the most ergonomic solution to always extend your eGraph implementation to your theory, but it's probably the most straightforward. Yeah.
Okay, then let's thank the speaker one more time. So if you haven't caught on yet, there's a bit of a theme to this session, and it's challenges around associativity and commutativity, and we'll be continuing on that theme. So please take it away whenever you're ready. Well, I can see, I see your desktop. Okay.
Okay. Yeah, so it's about preprocessing your EGRAPHS. So you can just take the normal EGRAPH implementation, you can just take your normal rule set, throw a bit of preprocessing on it, and your rules get better. So let's start with the general goal. We have some terms like a times 2 divided by 2, and we want to optimize it. And we have the general rule set, like we can distribute multiplication and division, so we can move out the y in x times y divided by z to the right. Maybe times 2 is also a shift, and times 1 can be cancelled out, and x divided by x is just 1. And if we then naively apply the rules, we can just rewrite a times 2 divided by 2 to a is shifted by 1 to the left, and then we are done. No rules applies. However, if we are a bit more careful, then we see that there is a better application rule, namely by first moving out the 2 to the right, we have 2 divided by 2, we can remove it to 1, and a times 1 is just a itself. So we see already one problem in application, which is probably familiar to all of you who have worked with EGRAPHS. We need to be careful about the rule application order. A second problem occurs when we look at, for instance, the group axioms. We have here the group axioms. It's associativity, multiplication with 1 is again the identity, and if we multiply with the inverse, then we just get 1. And now we want to prove that the double inverse of A can be simplified to A itself. But to do this, we first have to multiply with the 1, so with the identity to make the term larger, and then we have to intelligently instantiate this 1 by the inverse of A times A, and only then we can regroup to the left, have double inverse of A times inverse of A, can eventually simplify it to 1, and 1 times A can be simplified to A. So here we see another problem. We have to get creative. We have to, first of all, think about that we can multiply with 1, and then we have to instantiate this 1, and there are infinitely many instantiations. And computer scientists invented multiple ways to solve these problems. I want to focus on 3. The first one is the manual approach. Just get a few heuristics together, how you can rewrite, and apply them. It's very fast. You can do this in milli or even microseconds, but it needs an ordering. It needs good heuristics, and if you aren't careful, then you get stuck, like we have seen with this left shift example. The second one comes from automated reasoning, and it's one aspect we will focus in the next few slides on. It's Knuth-Bendix completion. You take your rule set, you complete it. We will see what completion means. And then you get a better rule set out of it with more rules, which you then can apply. It's confluent. That means you can apply it in any order, and it will produce a normal form. However, it not always works. There are some failure cases. It theoretically can apply to arbitrary rules, but sometimes it runs on forever, which is not that practical. And it's undirected in the sense that for EGRAPHS or manual rewriting, we have a term, we want to optimize it, we apply rules to it. Knuth-Bendix completion works before we have terms. It just works on the rule set, and it combines them in an arbitrary order and produces more rules. And the third aspect, which is currently state of the art, is EGRAPHS. We apply rules, we save all possible rule instantiations we have found so far, and then we explore basically the state space of all rules and pick the best one out of the set we have found. There are a few small problems. For instance, it's incomplete. This double inverse of A example in the group axioms, it will never find it. It will see, okay, there's no rule which applies. So maybe, depending on how you write your rules, it can multiply with 1, but that is all it can do. It will never instantiate this 1 if you don't say it how to instantiate it. And it tends to explode. So it tends to enumerate all possible terms, and then your computer crashes because you're out of memory. So our idea is, let's combine the two. Let's combine Knuth-Bendix completion with EGRAPHS. The idea is Knuth-Bendix completion takes a rule set and somewhat completes it. So let's complete our rule set and then throw it to the EGRAPH with our extended rule set and see if it can manage to do better. So first, let's look at a short primer on Knuth-Bendix completion if you haven't seen it yet. The idea is we have 3 simple rules. The orient rule, deletion and deduction rule. Orient means if you have an equation s is equal to t, and we know that by some order, usually one takes the Knuth-Bendix order, but it can be more or less an arbitrary order. If s is larger than t, then we can orient it into a rule which just rewrites s to t. So we just take one orientation of the equation. Deletion says we can simplify our rule set if we have just a reflexivity rule where both sides are equal. And deduction, this is the interesting rule. We can just add new rules if s and t are a critical pair. So in the previous talk, critical pairs were already mentioned. Now we will look at an example what they are exactly. So let's take our group examples, so the 3 group axioms. And in the first step, our algorithm would just apply orientation and would say, okay, so in the first example, maybe oriented from right to left to move the parenthesis back to the end of the term. In the second example, x times 1, which is a larger term than x, so we will orient x times 1 from left to right, and also x times inverse of x can also be oriented from the left to the right to just simplify our terms. And now we find a critical pair. A critical pair, you can take a look here, is for instance this term, which taken the the left-hand side of the oriented associativity rule, and it tried to overlap this part x times y with our inverse rule. So it overlaps x with x and inverse of x with y, resulting in the terms x times inverse of x times z. And on this term, both rules apply. So we can apply the associativity rule to move the parentheses to the right, or we could apply this cancellation rule to replace the left-hand side with a 1. And because we have applied correct rules to this term, we know that both resulting terms are equivalent. Therefore, we have a new rule which says x times inverse of x times z is the same as z. And then the normal orientation rule applies, oriented from left to right. And with this new rule, it continues. We again form a critical pair, again with the cancellation rule. So on the right-hand side, we instantiated z with the inverse of x. Again, both rules apply. So with the cancellation rule, with the normal cancellation rule, the right-hand side cancels out to 1. So we have x times 1, which is the same as x. On the left-hand side, and with the other rule, with our new rule, which is this one here, we know this whole term is the same as z, so it's the same as 1 times inverse of x. And if we orient this rule, you can see, okay, we are already very close to the rule we want. We have 1 times the double inverse of x is the same as x. So we have invented a new rule which we previously were missing. And then it goes on, and we'll find that 1 times something is the same as something, and eventually we find the rule inverse of x is the same as x. And now we could rewrite the example from the first-hand slide. So generally, Knuth-Bendix completion guarantees us a few things. So if our order is a reduction order, which means it's a strict partial order which is well-founded and stable under substitutions, then if Knuth-Bendix completion terminates, it produces the confluent and terminating rewrite set, which is complete on every ground term. So we can basically prove every equation we want. So we will find a normal form for every term, and we can apply our rules in any arbitrary order we want. However, there's this word if it terminates, which is a bit of a restriction because, for instance, for commutativity it won't terminate. There are extensions like unfailing Knuth-Bendix, which eventually produce every ground instantiation of rules, but generally it will run forever. So our idea is, okay, let it run a bit. It will go closer to a confluent rewrite system, and we hope that our partial system in between is confluent enough and has good enough rules. We will make this good enough a bit more precise in the evaluation section. So I mentioned there are a few opportunities. Namely, we can find 2 new kinds of rules. The first one are shortcut rules. So in the example where we have some a times b divided by b, we can apply our rule which moves the b to the right. Then we have a times b divided by b, and then we can use this rule b divided by b is 1, and then we can use times 1 is the same as just the left thing. So we can apply 3 rules, but with Knuth-Bendix completion we will get a rule which expresses all these 3 rules in one rule, which just says a times b divided by b is a. So there are a few shortcut rules which might help to bridge the explosion gap of EGRAPHS, because it will in shorter time find better terms. It will directly skip a few rule applications if the term matches, and therefore it won't pollute the memory of our computer so much. And more interesting, on the right-hand side, we have new rules, like this double inverse rule with the group axioms, which were previously not present in our EGRAPH. So we have truly more power than our original rule set had in the EGRAPH. Given that, let's look how we do it. So we have a relatively simple algorithm. First of all, so we first run Knuth-Bendix completion. Here it's step 2. I will talk about step 1 shortly. So we run Knuth-Bendix completion using the tree equational theorem prover to obtain a few critical pairs and the resulting rules. And until we have obtained n rules, so if we have obtained then n rules, n could be 100, so after obtaining 100 rules, we orient on our rules, and there we tried different modes. For instance, we could say, okay, take all new rules and only the new rules and then go with it, or take the new rules and re-add the original rules we have from the eGraph back in our rule set. This is important because, for instance, some rules like x times 1 is the same as x are sometimes applied in both directions in eGraph. So we not only want to simplify x times 1 to x, but also sometimes we want to multiply with the 1 to have x goes to x times 1, and then maybe more rules apply and can simplify it. So sometimes you might want to keep our original rules even if they are oriented against the intuition. And then we just run the eGraph algorithm on our new rule set. And we also tried a greedy algorithm where we just apply the first rule that matches, and in the sense that if our reward system is somewhat confluent, then it shouldn't matter in which order we apply the rules. And then I have also this first step, which is filter, because I mentioned there's a problem with commutativity where we can't orient commutativity, and therefore we can only work on concrete instantiations which we can orient. So we also tried, okay, if these rules make a problem, just take them out. So to the interesting part, what does the runtime say? So on the left-hand side, we have a log scale block for time. So we tested at 10,000ths of a second, thousandths of a second, up to a second of time, with different rule sets. So in blue, you see the base rule set, which starts in 10,000th of a second, roughly at 10 symbols, which are simplified. So we get a large term. We apply the rule set, and turns out the eGraph can cut out on average 10 symbols. And if we give it more time, it goes up to, and eventually it can go up to 13 symbols can be cut out of the term with the normal eGraph rule set. And then we have a few comparisons, for instance, with Knus-Bendix completion. If we just take the Knus-Bendix completed rule set, we see if we have basically no time at all, we are a bit worse. But as soon as we get 1,000th of a second, or yeah, this should be roughly 1,000th of a second, then we are a lot better than the eGraph. So we, in the same time of 1,000th of a second, we managed as much as the eGraph managed in 10 times the amount of time. And eventually we managed up to 14 symbols reduction. And yeah, we also tested out this no unorientable rule set. So we cut out this commutativity rules. And it turns out if you have enough time, it's worse. It doesn't manage to prove as much as the extended or KBC rule set. But if you have no time, so if we basically just run a few instantiations of a rule and then extract the best term before the eGraph has time to explore really, then these no unorientable rules are a lot better than basically all other rule sets, probably because they are more confluent. The rule set could go more in the confluent direction because they didn't have these unorientable rules, and therefore it managed to optimize more. Then on the right-hand side, we have the idea followed through. So let's say if our rule set is somewhat confluent, just apply it greedily. And it turns out if we have no rules, it's quite bad, so around 7 rule symbols. And if we then go larger, we see, okay, it simplifies more and more if we have more rules, up to 2,500 rules, where it reaches roughly 11 symbols of reduction. And the best is with the extended rule set in this case. And if we remove the unorientable, then we are in the lower two cases. So greedy needs unorientable rules. We make sure that we only apply once to not run an endless loop, but they seem to help together with some other rules. But overall, we see the greedy rule set can't simplify as much as our original rule set. So we are 11, and 11 is roughly in the middle of the left graph. So greedy is still a lot worse, even though our rules make it better than before. Okay, this slide. Sorry for there's a small problem with the slide set. Okay, and if we look at the rule set number in the EGRAPHS setting, we have this picture. So we see that if we have basically no rules, we have the same curve from before. We've managed around 10 symbols in no time, and eventually we manage up to maybe 13 symbol reduction. And if we add more rules, it gets better, except if we go above 100, then we are in the yellow and gray lines, which means if we have less time, more rules doesn't really bring anything because they pollute the memory and pollute the space. Therefore, we don't manage to explore so much. We stay basically in the same term set, and therefore we can't find the good terms. Only if we then have enough time, we again find good terms. So we found that around 100 rules is the sweet spot for our completion. In our ongoing work, we look at conditionals. So there's also a few sections in the extended abstract, which is on the web page, where we looked at what can we do with, for instance, division, where we want to make sure not to divide by 0, and then one has to be a bit careful because Knuth-Bendix completion usually doesn't have conditionals. One could split it, or one could add if rules, and we explain it in the paper. Another is how to reorient these rules. For instance, another option we are currently looking at is just make all rules bidirectional where it's possible. So we find rules by Knuth-Bendix which are oriented, but maybe the other orientation is more helpful to explore more rules. But our preliminary results say it just explores the EGRAPHS faster. And another very interesting direction is to move the Knuth-Bendix completion into the process during the EGRAPHS. So while rewriting in the EGRAPHS, maybe just use critical pairs between the rules we really use and skip all the unnecessary rules which Knuth-Bendix would otherwise explore. So to conclude, just pre-process your rules with Knuth-Bendix completion. It finds better results faster, so it finds the same result in faster time, and it sometimes even finds more results because it adds novel rules. And even with Knuth-Bendix completion, greedy stays worse than EGRAPHS. And in the future, we want to look at a bit more how can we select the critical pair rules. Currently, we just use the ones that tree spits out in the order tree spits them out, but there might be some gems in there and a lot of garbage, so we want to be a bit more selective. Okay, thank you for your attention. I'm happy to take questions.
Thank you. Yeah, we definitely have some time for questions.
So can we look at the first slide, very first slide?
Yeah. Okay. Then
Yeah. So I want to see the both example. Yeah. So Knuth-Bendix completion is well motivated if you are writing a single term instead of term bank, because if there is no non-confluence, if there's a critical pair and you take one path, then you lose access to the other part. But it seems to me that this motivation doesn't really apply to EGRAPHS. So for example, for the example on the left, EGRAPHS have no problem just doing this derivation because it is not throwing like one half of the critical pair away. And for the example on the right, so you write x times 1 equals to x, and usually when people apply xset, they will put both directions of the equation as a rewrite set to do xset. So EGRAPHS has no problem deriving the example on the right as well. So I think like I would need some more motivation to make it convincing to me that Knuth-Bendix completion actually is beneficial for EGRAPHS. So this is my first question. And the second question is, yeah, of course, due to your evaluation, you see there's some improvement. But I have a null hypothesis. So if you do null-span-disk completion between two rows L and R, you are kind of inverting one row like L and composing it with R. So doing null-span-disk completion to resolve a critical pair L and R is sort of like adding a row inverted L composed R to your rewrite system. So I have a null hypothesis that all the improvement you are observing are just effect of rule composition. So you are making some rule that effectively do multiple rewrites in the original rule set. So I think like to reject or prove the null hypothesis, I would want to see like what happens if you just do ordinary rule composition and see and see if that preprocessing already enhances your rewrite set. So that means like you have a bunch of rules and you just sequentially composing them and add them to the rewrite set. And does this provide improvement? How does this compare to null-span-disk compilation?
Okay, thank you for the question. First, to the first part of your first question. So yes, in the sense, so it was about eGraphs for both paths. In that I agree, because the left-hand example is solved by an eGraph, and so there it was more about maybe we can with null-span-disk completion just skip eGraphs and do greedy rewrite, which the eval turned out wasn't the case. And so now onto your second question, it was about shortcuts, and if basically all we find are shortcuts, all rules. And yeah, so one could postulate these shortcuts don't really help much. I can't prove or disprove if these shortcut rules, which are implied by other rules, help or not. One would need more experience. But I at least can say for the second example, an eGraph is never able to optimize this term. So if we add both directions, so we can add both directions for the first and for the second rule. For the second rule, it would basically, because it says x goes to x times 1, it would grow our eGraph quite fast, because every node in every E class we would have a times 1. So, well, it grows at least a bit. But we would find this rewrite from going A inverse inverse to A inverse inverse times 1. But we can't add this rule, x times inverse of x to 1, in the other direction. Because in the other direction, we would need to instantiate x with arbitrary stuff. So we could add it for the concrete instance, A times inverse of A goes to 1, or B times inverse of B goes to 1, or inverse of A times inverse of A goes to 1, or in the other direction. So we could add concrete instances, but generally we would need all of these instances to rewrite some double inverse. So if we have a more complex term with a double inverse, we would need this complex term inside the rule instantiation, which would blow up, well, basically it's the whole Herpra universe in our rule set. I hope this answers the question.
So I think now I get it. So
I think we should maybe take the rest of this question offline.
Okay.
We do have time for maybe one more quick question, if anyone has any.
Hello, I have a short question. I assume there should be an order for KBC to work on your rule set. Maybe that's already in your talk and I missed it, but could you explain, like, is there is it rule set by rule set, or you have a common method to determine such a order you're going to use?
Yeah, so it was about the question about the rules, about the order in null-span-disk, and the order needs to be a reduction order. That is, it's a strict partial order which is stable under substitution. So whatever we substitute in our rule, it has to the order has to be preserved, and it has to be well-founded. So then for that, every order which fulfills it works, and one common order is the null-span-disk order, which just says, which is basically or very similar to a lexicographic path order, where we go through the term, we have a precedence on our function symbols, which can be arbitrary, but one could also say, for instance, multiplication is more expensive than addition, And so this order, so this GNU index order can be, for every signature, it can be derived, and it works always.
Okay, and with that, let's thank our speaker one more time. Okay, and now we'll transition to the final talk of this session, where Sophia Bricky will be presenting remotely, and I think that is queued up.
Yeah, I can hear you. Oh, did I stop screen sharing? Sorry. Screen. You see that? Is that all good?
Hi, Sophia.
My handheld mic.
Hi, Sophia. Can you hear me?
I've only got this microphone. Okay. Hi everyone. So my talk. This is a presentation about my master's thesis on EGRAPHS modular theories. A lot of this talk is going to be for specifically the theory of AC. I will maybe talk a bit about why later, but so you can also think of this as EGRAPHS modulo AC. So here's how I like to think of EGRAPHS. You can think of it as sort of three layers. The bottom layer sort of handles ground atomic equations. E1 is equal to E2, E2 is equal to E3, so we should figure out that E3 and E1 are equal. And then on top of that we have congruence closure, which handles the non-atomic equations where we have function symbols. And then the top layer is equality saturation, which handles identities, which are universally quantified equations. Yeah, so and the way the top layer works is if we have some universally quantified equations, we try and look for instances. And if we find an instance, we might have to add the other side of the equation if it doesn't exist. And this is the thing that oh, sorry, it's a some toy that I stepped on. My apologies. And then we might have to add the other side. This is what blows up the graph. And so AC is a particularly notorious case of blowing up the graph because, and in particular, commutativity is fine. But if you see an associativity, we sort of have to generate this new E node potentially if it doesn't exist on one side of the equation. Yeah, so I'm going to focus on A and C together. I'll talk about why not just A by itself a bit later. But AC is very common and it's a problem. So there's often you often have AC plus other stuff, ACU abelian groups. So just some examples. Here's A plus B represented as an E-graph. Here's A plus B plus C represented as an E-graph and run to saturation under AC. And A plus B plus C plus D. And yeah, you see it gets bigger. Someone asked me if, when I have given this talk previously, someone asked me if these were hand generated, and hopefully you can figure out the answer based on this. This is some size 8 term, a small window of it, A plus B plus C plus D. Run to saturation under AC. So obviously it's an exponential explosion. There's 2 to the n E classes and n times 2 to the n E nodes across those E classes, I believe. I've gotten those combinatorics wrong before, but I think that's correct. Yeah, so solutions or non-solutions that have been mentioned in the past. One non-solution is to fire rules less and less if they're used too many times. So if we run associativity 100 times, then we decrease its weight, try fire some other rules. And yeah, this isn't. So firstly, this doesn't help if you intend to run to saturation, which is what you have to do if you want to be guaranteed to find everything. And it can slow down finding the equations you want to find because maybe there's some necessary use of A and C that you're sort of, missing out on by, well, not temporarily missing out on using. So here's just sort of an example of the kind of reasoning we might want to do with AC, a very simple example. So we imagine some function that satisfies this identity. It's an affine function, if that means anything to you. But the upshot is if we have f of something plus f of something, we can sort of merge that into one f, but we also get this extra constant on the outside, this plus 1. So we start with 3 f's added together. We should be able to do 2 merges to get this plus 2 constant on the outside. But to do this, we sort of need a few steps of associativity, depending on how we represent the starting term. And here's the online egglog demo. I quite like this graph because you see there's this, it's very hard to see at this scale, but it's generated the constant 2, but hasn't really found where to put it. So it's sort of, spend most of its time just sort of reassociating and commuting the plus nodes. So SAT people have added theory-specific solvers and made very successful SMT solvers. So why can't we sort of handle AC in a specific way using this idea of theory-specific techniques rather than relying on the general, powerful, but potentially the slower equality saturation? That's the motivation, at least as far as I can see, for the name EGRAPHS modulo theories. So yeah, it's a natural idea to consider working up to AC in your EGRAPH somehow. That's been thrown around for a while. Philip Zucker gave a very nice talk on it last year. But there's some problems with, there's some technical issues that need to be sort of ironed out to make this work properly. So here's an example of how we'd like it to work, right? We'd like to think of plus as variadic. So in our example of 3 f's added together, we just think of it like this. We don't have to worry about which way to associate it. And then we run that affine function identity a few times. And eventually we hit saturation like this, and the thing we wanted to find, A plus B plus C, variadically added together here, f applied to that, and then plus of that with 2. That's our desired term, represented in this very compact final graph, which is saturated on that rule for affine functions. So that's what we'd like to do, but there's sort of a gap in this thing, which we go back to an even simpler example. A plus b equals b, so here's a. If you add b to it, you get b. The arrows kind of point a bit weirdly, sorry, but if you add a to itself, you get c, and if you add c and b together, you get d, right? And so what we would like to show is that b, we can expand b into a plus b, we can expand this b again into a plus b, right? So we get a plus b. Then we reassociate, and then we collapse a plus a into c, and we collapse c plus b into d. So this is b should equal d, right? This is the chain of reasoning we would like to our EGRAPH to represent. But you sort of see that we're sort of stuck, right? There's no extra rules. We've sort of represented everything up to AC, but there's sort of, you know, we've represented everything up to AC, but we've sort of missed this consequence of the theory of AC, which we should have merged this E-class and this E-class in this E-class. So just making the sort of E nodes work up to AC, just thinking of this variadic and commutative, we've lost the equational reasoning required to actually properly handle AC. So we have an E-graph closed under congruence, but it's missing the desired equation. So we could add back some saturation step, but that sort of unsolves the problem that we were trying to solve in the first place. We don't want to just blindly saturate, we want to do something more clever. So this is my contribution, although it's based on work that's existed previously. So what we want to do is we want to think of adding this AC closure thing in between as a sort of in-between layer. It's more complicated and more expensive than congruence closure, but it's sort of less expensive than the general procedure of equality saturation, which works for anything, but is sort of slow for AC in particular. And so the way that AC closure works, well, we sort of look to rewriting systems. And so if we think of an E-graph, we can think of it as a rewriting system, just like has been pointed out in previous talks. You know, G of EA, G applied to EA gives us E1 if we call this class E1 and this class EA. You can read all these things off the graph, and there's a bunch of more complicated ones. And you see that, for example, H of EA and E2 rewrites to both E3, but it also rewrites to E4, right? And so the way E-graphs do congruence closure is they see that we've got something that rewrites to 2 different things. And this is a critical pair, so we can E3 and E4 are both equal to the same thing in the middle, right? If we ignore the direction of these rewrites and just think of them as equalities. So we conclude that E3 is equal to E4, and then we can resolve that critical pair by merging E3 and E4. That's how congruence closure works. So to do AC closure, we need to find AC critical pairs. So in our example, we had this sort of, these 2 central terms are equal up to, well, A, more generally AC. And so from these 2 things being equal, we learn eventually that C plus B and A plus B are equal. And C plus B was also, we could continue this further, C plus B was also equal to a D on this side, and A plus B was equal to B on this side. So the way AC closure works is you find an AC critical pair, T1, you know, with some term that doesn't have to exist in the E-graph, just some term that could rewrite in 2 ways. And we take the equation that we find and orient it into a new AC rewrite rule, like this. And we introduce the new rule with the old ones. And so there's actually some design choices here. So this is, the way I've just described, I'll call it the side table approach. We don't store the plus nodes in the normal E-graph at all. We sort of have a side table of these AC rewriting rules where we have, you know, some AC term rewrites to some other AC term. And so when you would go to add E1 plus E2 to the E-graph, you create a new rewrite rule like this for some fresh E3. And then when we find a sort of unit rewrite rule in the AC part, the AC table, we sort of feed that back into the original E-graph. The alternative approach is this sort of integrated idea where you think of plus nodes as any other E-graph node, but you look for critical pairs as some separate step, right? But this is a more integrated way to think of things. I didn't think too hard about this trade-off when I implemented it, but they should be equivalent, you might think, but there's sort of a non-obvious thing that you might miss if you went with option 1, the integrated approach. So the integrated approach, if we had some equation, we'd generate a new symbol E, so new E-class ID for them, and put them into those E-classes. And it's this approach is more eGraph-like because in normal eGraphs we always have rules that are like this. Some function applied to something goes to E, but we never have a rule that some function applied to something goes to some other function applied to something. But yeah, so they're equivalent only if you pay attention, because in the side table approach, if we build this, if we make some new rewrite, E1 plus E2 goes to E3, and we have some existing rule that has E1 and E2 in it, then we can compress this existing rule down like this, right? The E1 and E2 have been merged into E3 now. And so essentially our algorithm is equivalent to Bookburger's algorithm, a standard algorithm in computer algebra. And so if you the side table approach connects very nicely to the textbook Bookburger's algorithm. But to make the integrated method equivalent, we need to do some kind of destructive rewriting to do this compression step, right, of introducing existing rules with new rules that appear. And it's maybe a bit alien for us eGraph people to think of this sort of destructive rewriting step of compressing down existing E-nodes, but yeah. So they are equivalent, but you have to be aware of this. Otherwise, you sort of get problems with explosion again. So some results. So I have an implementation of this. As some toy examples, I generated random identities. I don't think that's a very representative sample maybe, but it's the best I have. And I ran to saturation, which for many identities, it doesn't hit saturation because there's some infinite loop. But we compare handling AC either with our sort of modulo theory approach or just via AC saturation, just running ordinary saturation on AC identities. And then we measured the final size. I just added together basically every measure of size I could to make it as fair as possible. And here's the final graph. So you see that here's the size with AC completion, the modulo theories approach, versus the size with AC saturation, the sort of traditional approach. And you see that all these green dots under the line, that's where the AC completion is smaller than the AC saturation. I chose to measure size rather than performance because I don't think my implementation is very well tuned for performance. But I would like to eventually do some other forms of benchmarking to compare them. But you see that generally AC completion is going to be smaller than running to saturation under AC, and you can kind of see as it gets bigger and bigger, you sort of get more and more savings, right? Than the sort of potentially exponential blow up you would have with ordinary equality saturation on AC. So AC closure is just a form of Bookburger's algorithm, and a well-known algorithm from computer algebra. Lots of work has been done to optimize it, but unfortunately, the problem is fundamentally E-space complete. So solving this gap, as I put it, there's no magic wand to solve it. You still need to solve a hard problem in the sense that it is E-space complete. Obviously, we hope that we can do it fast enough in practice. Now, so we're moving on to the more general case. Filling the gap, as I've termed it, is exactly equivalent to a well-known problem in algebra, which is the word problem. So for just associativity, the word problem is undecidable, so we can just have some A closure step as a neat little package. We could maybe have an A closure step that we feed it some number of steps and it goes to that number of steps, but there's no guarantees that we'll ever reach the end. Some word problems are much better than the E-space thing we have for AC. So if you have inverses and you get polynomial time, and then once you can have some sort of nice things that include division and things, then we get the word problem can be done via Gaussian elimination, which is a very well studied problem that's not just polynomial time, but a small exponent in the polynomial. Bookburger's algorithm, there's a lot of variants you can make of the same basic idea to handle other things, idempotence, inverses, all that sort of thing. Indeed, so this basic idea of AC closure already goes back to the rewriting literature by, among others, Tawari and Kapur, who have given some sort of variants of this. So this particular this particular thing is not new. It's more the application of this idea to the EGRAPH world, and in particular, I want to point out that this closure, AC closure or ACI closure, or whatever you want to do, is sort of fundamental to solving the problem in a complete way. Otherwise, you're sort of missing some of the power, or missing some of the consequences of the theory you're trying to work with. Yeah. So. Just a couple of notes that I won't go too in depth into this, but there's the problem of matching modular AC. This is the sort of thing I actually started on before realizing that there's this completeness issue of just working up to AC without doing this extra AC closure step. I'll kind of skip over this quite quickly, but you can think of matching as kind of like a rewriting problem, right? So you can think of if this is our EGRAPH, for instance, we have this pattern, there's a way to think of the pattern as its own sort of weird rewrite system. And I mean, we don't even need to think of it as a rewrite system. It's just a relation. What we are doing is we're sort of interleaving the relations in a certain way. But thinking of it as a rewrite system, then matching is sort of resolving critical pairs, right? So this sort of thing is you'd have one branch, which is like the EGRAPH relation, and one branch, which is the match relation, and you sort of find a critical pair to get that. You annotate some E-class with some match state. And so hopefully, I hope, obviously I'm skimming over this quite a lot, but I hope that you can generalize this sort of setup to explain what AC matching should do, and explain, hopefully it terminates in the general case as well. So yeah, so that's tentative work that you can do AC matching in a hopefully always terminating way by orienting rules to handle what would otherwise be a potentially infinite match space. So I'll explain the infinite match space problem. This a plus 0 equals equal to a. So if we wanted to match the pattern a plus x, well, x could be 0, or it could be 0 plus 0, because you can sort of feed this back into itself, reassociate, and then you get this, substitute this a here for a plus 0. You get a plus 0 plus 0, and then reassociate, and you can do this infinitely many times. So the space of matches is infinite, but hopefully with a sort of this rewriting approach, you can find some sort of finite minimal set of matches that kind of represent the entire space. And a brief discussion of future work. If we just want to match, for example, this pattern, there are a lot of ways you could match this against this term, a plus b plus c plus d. But probably, in this case, we might just be looking for any case where there's 4 things added together. So there's sort of a lot of redundancy in this space of matches as well. So one way to deal with this, just some trick that I've found in existing literature, we might have some ordering constraints. So we could say that the substitute of whatever is substitute for x has to be less than y, has to be less than z, and that sort of cuts down the potentially combinatorically big space of matches. So yeah, I started working on essentially the matching problem here, and realized that without AC closure, EGRAPHS modular AC are not very useful, because you're sort of throwing away some of the consequences of the AC identities that you'd want to find. And yeah, so please look at my upcoming thesis for more details. I'm not sure how fleshed out the matching part will be, but the working modular theories and the sort of word problem or AC closure idea is very well fleshed out. So yeah, thanks very much. And I've got plenty of time for questions. So.
I think I will have to ferry them to Sophia. Okay, so I will attempt to do that. So we have time for a couple brief questions before lunch.
Thank you for insightful presentation.
Keep it short because I'll have to repeat it. She cannot hear that.
Oh, so I speak like.
Just speak it. And I have to memorize it and then repeat it.
So to my understanding, the Booth-Burgers algorithm can be built as just a specialization of Nuss-Bendix algorithm to polynomial ring of the linear fields. So I think the wording of using Buch-Balger's algorithm is too narrow here, I think. So in exactly what sense do you refer to Buch-Balger's algorithm instead of Knuth-Bendix's algorithm?
Okay, thank you.
Yeah, sorry, if you could just repeat the full question. Yeah. Mhm. Yeah. Yeah, so I mean, I guess there's a few things to point out. So the first thing is it is a specialization of both Knuth-Bendix and Buch-Berger's. The first thing is that if we want to generalize to things beyond AC, if we want to work with polynomials, rings, that sort of thing, then the more general version of Buch-Berger's can handle that just fine. The other thing to note is that Buch-Berger's algorithm, as a specialization of Knuth-Bendix, always terminates, which is very nice property to have. So obviously you can think of the general notion of EGRAPHS modular theories where you have some general Knuth-Bendix thing, but that doesn't really give you anything in the sense that Knuth-Bendix is just solving the same problem that equality saturation is solving by sort of instantiating identities and so forth. So we're kind of looking for a nice terminating subset, and Buch-Berger's is one such subset that handles general polynomials, and even within that we can focus on AC, or if we are working with some rings or polynomials, we can use the bigger algorithm. I hope that makes it clear. Okay. Yeah. Thanks, everyone.
Everybody, I think we are hitting quorum. The room is filling up, so I think we should get started with the next session because it is full as well. Okay. Yeah, thanks for coming back, and yeah, please, I think everything is set up, so please take it away when you're ready.
Working? Okay. Great. Okay. Okay, well, good afternoon, everybody. My name is Rupanshu Soya. I'm a CS PhD student at Stanford. This is joint work with Xiantan Hong, Yihong Zhang, and Alex Aiken. So we call this project Rewrite System Showdown because we're trying to do the first rigorous comparison of equality saturation with another program optimization technique. And this is in reference to a PLDI paper from 1995, which does the same thing for software pipelining, which I recommend if you're interested. Okay, so EGSAT, of course, extremely popular, egg and egglog, and now many other implementations for different languages like Python, OCaml, Common Lisp, Haskell, what have you. And the number of projects that are about EGSAT or use EGSAT are simply too large to fit on a single slide anymore. And just anecdotally, it is very common to see at top PL venues a couple of papers that are about EGSAT or trying to invent a variant of EGSAT. I think at this PLDI there are 5 by my count. My point is that our community really cares about this technique. However, EGSAT has a number of famous limitations. So it has trouble with AC rules, which can blow up the eGraph. Things like variable bindings are hard to represent. Control flow is hard to represent. Optimal extraction can be really slow. And not to mention things like optimistic analyses, context-aware reasoning, or parallelizing EGSAT. However, very interestingly, instead of moving us away from EGSAT, these limitations have had the exactly opposite effect. These limitations have engendered a flurry of papers that explore variants of eGraphs in an attempt to fix some of these problems. And this is an exciting and rapidly progressing area. And just today morning, we saw several papers trying to add AC theories to eGraph. And so this work is by no means done. So there's more work to do for making EGSAT more scalable, better suited to certain class of programs, etc. However, let us take a step back. Why are we doing this in the first place? Why do we use EGSAT at all? I would claim that people use EGSAT not because it is fundamentally better than other program optimization techniques, but because of more practical reasons, like frameworks like egg and egglog are really easy to use, and EGSAT is now extremely popular. But nobody seems to have done an extensive comparison to actually determine if EGSAT is the right tool for their problem. Is there an alternative? EGSAT solves a certain kind of problem. Are there other methods to solve the same problem? Well, EGSAT is not the only one. Perhaps the main contender is stochastic search. So I'll give you a 101 on stochastic search. Instead of maintaining an eGraph of equalities, we're going to maintain a single concrete term at a time. We're going to have the same rewrites as equality saturation, but we're going to apply these rewrites probabilistically and in a cost-guided manner. So you might start with some term like this, and with some probability you might transition to some new terms like this, and you can just keep doing this. This is not a very intelligent approach, but you can do this extremely quickly, and you can scale this. This process is embarrassingly parallel. So if you have 128 CPU cores, you can scale this to 108 CPU threads. So this is a very powerful technique, and it solves the same kind of problem that EGSAT solves. Furthermore, egg's interface is very general, And the same interface can be implemented by stochastic search. So E-class analyses, for example, can be implemented for stochastic search just by porting the analyses to work on like concrete terms instead of E-classes. So what we do in this project is we write an implementation of stochastic search that follows the same interface as EGG. And then we do an extensive comparison over a number of benchmarks to see which one wins. Okay, so now I want to discuss our 5 benchmarks. So our goal is to cover a variety of use cases. So we're going to see some benchmarks that are small, self-contained applications, but then some like larger, substantial ones taken from prior work. And so when we run EGSAT and stochastic search, we're going to give them both the same amount of wall clock time, but we're going to run stochastic search with 128 threads. But EGSAT is run with only a single thread. So this gives stochastic search more CPU time, but not more wall clock time. And we would argue this is a fair comparison because the algorithm is just embarrassingly parallel. Okay, so let's see our first benchmark, which is a small self-contained application. This is the classic matrix chain multiplication benchmark. So say you have 3 matrices of different sizes, but which are compatible. Say you want to compute the product, ABC, of the 3 matrices. There are 2 ways of associating this product. Which association minimizes the number of scalar multiplications? So this is what we want to do. Like given some large product of matrices, we want to find how to carry out this product so that we minimize the number of scalar multiplications. So we're going to solve this problem using EGSAT and stochastic search, and we will compare the solution quality obtained by both approaches. Another good thing about this benchmark is that there's a fast polynomial time algorithm to solve it. So we can just find the optimal solution, and then we can see how close to optimal both techniques can get. Here are the results. So on the x-axis, I gave the number of matrices in the test case. This is randomly generated. And on the y-axis, I gave the ratio of optimal cost to cost found by either technique. So you want to be as close as possible to the y equals 1 line here. So we see that until about 300 matrices or so, both techniques are extremely close to optimal. But as we go above 300 matrices, EGSAT just falls off rapidly. And this makes sense because this search space is just too large, and EGSAT doesn't have any cost guidance. So it just cannot figure out the right association in such an enormous search space. Stochastic search does well and stays almost close to optimal throughout all the test cases, because it is cost guided. Like every time stochastic search makes an association that drops the number of scalar multiplications, the search is reinforced in that direction. And so it can just hill descend to the optimal solution. I also want to point out one more interesting thing, which is that below 300 matrices, so in the regime where both techniques are about the same, EGSAT usually finds the optimal, where stochastic will sometimes find something that is only close to optimal but not exactly optimal. And this difference was about 0.3% in our experiment. So there is a bit of a difference in how they perform. Okay. Next benchmark. This is another self-contained application. We're going to do trig simplification from like your high school math class. So we collected 35 trig problems, such as proving this trig identity. The rewrite rules for this are going to be standard algebraic rules plus some like standard trig identities like the ones you see on the slide. And we're going to optimize AST size, so like a very simple cost function. So for each of the 35 problems, we have an intended solution which we literally took from the textbook these problems are from. And so I'm going to consider a problem solved if a technique finds a solution that is no worse than the intended solution in terms of AST size. Here are the results. So now I give stochastic search cost on the x-axis and EGSAT cost on the y-axis. So points on the y equals x line are problems on which both techniques found something of equal cost. Points below the line indicate problems where EGSAT was better, and points above the line are problems on which stochastic was better. So overall, 23 out of 35 problems were solved by both techniques. Then there were 3 problems that EGSAT solved and stochastic did not solve, and 3 problems that stochastic solved and EGSAT did not solve, and 6 that neither solved. Okay. So I guess overall, neither technique comes out to be Pareto optimal over the other. There's a core set of problems that both can solve, and then a few on which either one manages to eke out an edge. The third benchmark is, again, like a high school math thing, indefinite integration. So we're going to do 10 problems of indefinite integration, so like doing the integral of x cos x. So the results here are very similar. We have 6 problems that both solve, 1 that EGSAT solves and stochastic doesn't, 2 that stochastic solves but EGSAT doesn't, and then 1 that neither can solve. Okay, so again, like neither seems to be Pareto optimal over the other. There's like a core set that both can solve and then some outliers. I want to highlight one issue that arose in this benchmark. So a very productive rewrite rule for doing indefinite integration is the linearity of integration. The problem is that under the standard like AST size thing, from the eggs math example, the right-hand side is going to have higher cost than the left-hand side. And this is very problematic for stochastic search. If you have a cost increasing rewrite, stochastic search is not going to apply it very frequently. So this is going to cause problems for stochastic search. To fix this, what we do is we modify the stochastic cost function to square the subterm. And if you like stare at this for like 5 seconds, you can convince yourself that this changes the linearity of integration to be a cost decreasing rewrite. So the point is just that sometimes you might need to tinker with the cost function a bit to enhance the performance of stochastic search on some benchmarks. EGSAT, of course, does not care because it's not cost guided at all. Okay. So now we move to our 4th benchmark, which is a more substantial one. So this is a tool called Zelinsky, published in PLDI 2020. Zelinsky takes unstructured CAD programs, like the one you have on the screen, which represents 5 cubes placed in a straight line. And Zelinsky is going to decompile them into a more structured CAD representation that uses higher order combinators like folds and maps and so on. So we re-implement Zelinsky with stochastic search. We keep all the same rewrite rules and the E-class analyses. And actually, the total effort in porting this to stochastic search was only mild, because as I said previously, stochastic search can implement basically the same interface as EG. Okay. So here are the results. So again, I'm going to plot cost of stochastic on the x-axis and the cost of EGSAT on the y-axis. And so now we have 2,000 problems. And let's see, on about 600, stochastic and EGSAT are tied. So they found a solution of equal cost. EGSAT finds a solution of lower cost on about 800 problems, and stochastic finds a lower cost solution on about 700 or 730 problems. So EGSAT seems to have a slight edge in this benchmark. And this is not surprising, actually. Zelinsky's rewrite system happens to be ill-suited for stochastic search, and I want to explain why this is the case. So what you typically find in Zelinsky is you have a program like this, and it gets folded into a higher level representation that uses functional combinators. However, usually programs are not in this nice form. They're in some like other form. And before you can do the nice rewrite that folds it into a higher level program, you need to get all the subterms into the right form before the final rewrite can fire. And so this causes problems because you don't get a lot of guidance from the cost function before the final rewrite has been applied. So to illustrate the problem more, I'm going to consider an abstract rewrite system to model this problem. So say I only have 3 rewrites. A goes to B, B goes to A, and F of 3 B's goes to G of 3 B's. You can represent the system with these 2 cubes. So each vertex in the cube is a concrete term induced by this rewrite system. And then there is one step you can take from one cube to the other. Okay? Otherwise, you can always move from like 2 vertices of the same cube. In Zelinsky, what we're trying to do is we're starting from the F3A's vertex, and we're trying to go to the G of AAA vertex. And this is really so imagine that the cost function that is guiding stochastic is like 1 everywhere but 0 only for the end vertex. So there's like no guidance at all. And so basically what's going to happen with stochastic search is it's just going to like wander around in this like left cube until it just so happens to get to the right vertex and happens to apply the one rule that gets you to the right-hand side cube, and then it will wander around in the right-hand side cube until it gets to the end vertex. So it just doesn't get a lot of guidance at all. And if you have a problem for which you do not have a good cost function that can provide guidance to the search at every step, stochastic is going to struggle. Whereas EGSAT can do this problem in like 2 iterations, actually. Okay. So our last benchmark is from a CC paper of 2022, and this paper uses equality saturation to prove inequalities inside the halide compiler. Okay, and so now we have about 6,000 problems, such as proving that max of I, 2 is less than max of I plus 3, 3. Here are the results. So again, it's the same kind of thing. We have a core set of problems that both techniques solved, and then a few that EGSAT solved and stochastic didn't, and some that stochastic solved, EGSAT didn't, and then a large set actually that neither could solve. And this is not surprising because it just so happens that the rewrite set in this paper is quite weak and therefore insufficient to prove every problem. Okay, so those were our 5 benchmarks. Let's take a step back and see what we learned. First, as I've been saying, neither technique is Pareto optimal over the other. Some hyperparameter tuning is required for both. For EGSAT, you may need to do some rule scheduling. For stochastic, you might need to change the cost function a little bit, or you might need to tune your restart schedule. I didn't discuss restart schedules in this talk, but you can see the preprint for more details. Stochastic is also more scalable. It really benefits from having 128 threads. Like the results are much worse if I run stochastic with like 10 threads. And the number of candidate programs that stochastic considers really does scale linearly with the number of threads. And then finally, another useful property is that stochastic uses constant working memory. And this is in sharp contrast to EGSAT, where the working memory goes up monotonically with time. So in this project, we looked at 2 techniques that solve the same problem. But to be more, okay. But like, which problem is it? So we call this equational program optimization. So traditionally, people only use EGSAT to attack this problem. But by decoupling the problem definition from its solution strategy, we can see that there are many more ways of solving these problems. In fact, there's a whole zoo of equational program optimization techniques. There's EGSAT and stochastic, of course, but you can do beam search, you can do A star, you can do greedy, or you can invent your own thing. Why are we limiting ourselves to only one member of the zoo? As a concrete example, consider pulsing, a technique that marries EGSAT and greedy search. So pulsing is a common trick in the literature in which the idea is that you do EGSAT for some amount of time, extract the best term in the eGraph, use that to seed a new eGraph, and you keep doing this until your budget is exhausted. And if you implement pulsing on the matrix chain multiplication benchmark, it really, really helps EGSAT scalability, as you can see. And EGSAT and stochastic search need not be enemies. They can be friends. They're part of the same zoo. So one direction I'm excited about here is, can we find a new technique that is Pareto optimal over the other by marrying their strengths together in the right way? So one example could be to do a little bit of stochastic search, find a diverse set of programs, and then do equality saturation on those programs so that equality saturation does not get stuck in local minima. And just as a parting thought, there is more to say about stochastic search. On the trig benchmark, if you implement a new secret optimization that I cannot tell you about right now, stochastic search actually beats EGSAT. And if you want more details, you should talk to my co-author Chantan, who's in the front row later. Thank you for listening. Thanks for your attention. I'll be happy to take any questions.
Thank you so much. We have time for a couple questions.
So you made a big deal in the talk, maybe an implication that the cost guidance is one of the main reasons stochastic search can, in many instances, outperform eGraphs. But then you pointed out that and that this also allows it to scale. What strikes me is that the clever part of EGRAPHS, the term canonicalization, doesn't really have anything to do with the cost guidance. You sort of pointed that out when you did the pulsing, which is a kind of cost guidance. Do you want to say a little bit more? Is there some utility to the canonicalization aspect that you could add to stochastic?
That's a great question. I mean, that is kind of the thing I'm hinting at. There might be techniques that are hybrids of the two. So maybe you do a little bit, you keep around an eGraph of the best things you've seen, but then you do stochastic search to find more things, more terms. So they're definitely, I don't know exactly what it would look like. I do think the canonicalization is helpful. But I don't have any results to ablate out the effect of the canonicalization from the other things. But I am definitely excited about doing hybrid techniques that get the best of both worlds.
So when you pulled up the indefinite integration thing and you talked about that little trick to massage stochastic search into using the linearity rule. So how much of this is dependent on the rule set? So maybe certain rule sets are better for EGSAT, certain rule sets are better for stochastic search, and you just need to massage the rule set into specific ways to make them work.
Yeah. So I don't have a good characterization for you for when a rule set is better for EGSAT and stochastic search. That is an interesting question. In all the experiments we did, we used all the same rewrite sets for both. So this is something we were careful about. Does that answer your question?
No, so it's just an open question. Maybe someone should.
Someone should.
Okay, I think we should leave it there. Let's thank the speaker one more time.
Uh-huh.
I don't know if there's a power on. Do you have enough battery to make it?
Start from the first slide, sorry. Just one. All right. Okay. Hello, everyone. The topic of my talk today is a new technique for jointly optimizing algebraic rewriting and instruction scheduling that I've been developing with Rupanshu and Alex. First, as a motivating example, let's look at prefix sum. We all know what prefix sum does. The question we want to ask is, what is the fastest algorithm to compute prefix sum of an array of length n on a processor that can execute m additions per cycle? Let's say n equals to 8 and m equals to 2. There are many ways to compute prefix sum. On the left, we have the naive algorithm for prefix sum. This computes prefix sum by adding inputs to the rounding sum one by one sequentially, taking 7 cycles to execute 7 additions. This network also happens to have the minimal number of adders among all possible 8 input prefix sum networks. Note that this network is completely sequential and does not use any parallelism. Recall, our processor model can execute 2 adds per cycle, so maybe we can do better. In the middle, we have the famous Coxstone network. This has maximal parallelism, and given an infinite number of adders, this is the fastest possible network. Observe that there are 3 clusters of independent instructions, so these execute in 3 cycles, given infinite numbers of parallel adders. However, note that this network has 17 adders, in contrast to the naive network, which has 7. The Coxstone network duplicates work to expose parallelism. Now, let's recall the problem statement about our processor. We can only run 2 additions per cycle. So the level drawn on the graph shows how the Coxstone network runs on our processor. It massively oversubscribes our processor because we can only run 2 additions per cycle, and this resulting in 9 cycle latency, even slower than the naive network. On the right, we have an optimal network on our processor model. The paper cited below constructed such a network and proved optimality, but using genius level of math only. Now, our technique is all about computing this automatically, and for general computation graphs, not just limited to prefix sum networks. Let's consider what is the requirement for every technique that solves the previously described problem. First, you need to exploit algebraic properties of the computation. Note that in the previous example, we are able to convert the sequential adder network to parallel ones only through application of the associativity law for additions. Then you need to be aware of the processor model. You need to consider the latency of each instruction. It also needs to consider how many instructions can be issued at once. As we have seen, the Coxstone network is optimal on processors with infinite parallel adders, but it's very slow on processors with only 2 parallel adders. Finally, it's also useful to handle heterogeneous resource, how many adders, how many dividers, etc. There might be multiple categories. Now, let's describe our technique, which is dubbed scheduling modular equality, or SME. The first part of the algorithm is standard equality saturation. We start with an initial program and apply equality saturation to build an EGRAPH that encodes all the knowledge about algebraic rewrites. The second part is novel and is our main contribution. We build an integer linear programming problem from the EGRAPH and the processor model. An ILP solver then solves the ILP problem and gives us the minimum latency schedule on the specific processor model. Note that the usual ILP extraction algorithm people talk about EGRAPH only handles minimal work schedule, which, as discussed before, is not aware of processor model and is not sufficient to find the minimal latency network on a specific processor model. Now, let's dive in the detail of the ILP encoding. We have 2 kinds of decision variables. The ILP solver is going to find out the values for these variables that satisfy our constraint and optimizes our objective function. First, we have a binary variable x n t for every e-node n and every time step t. This variable is set to 1 if e-node n is set to finished at time t. Then we have another kind of binary variable, yct, for every e-class c and every time step t. This variable set is set to 1 if E class C is finished at time t. When the ILP solver returns the value for these variables, the XNT is going to tell us exactly what operation or inode to run at every time step. Now, let's work through the encoding in English. Our objective is to minimize the finish time of the E class of the last instruction, or the root E class. The constraints are, first, the E class of the last instruction must finish, or the root E class must finish at some time step. And if an E class finish at t, that means one of its E nodes finish at t. That's how an E class got finished, because one of the E nodes that implemented it got finished. The third one the third one considers instruction latency. If an E node finish at time t, then all of its children E classes or argument E classes must finish before t minus d, where d is the latency of the E node or the instruction. And finally, we have the resource constraint. The resource usage of all E nodes active at every time step t must not exceed capacity. So we will have an inequality for every time step and every kind of resource. Okay, that defines the ILP encoding we are using. Now, let's see what we have gained from all of this. Here are the throughput measurements of the generated schedules on my laptop, which has a CPU with Kaby Lake architecture, kind of an old one. According to the information I found, the addSS instruction has a latency of 4 cycles and throughput of 0.5 cycles. And that means we can run 8 parallel addSS at once. We use SME to optimize the naive instruction sequence, and then we measure the throughput in terms of average cycle per processed element for the naive instruction sequences and the SME scheduled instruction sequences. First, observe that for small input size, smaller or equal to 3, there isn't any instruction level parallelism to extract, and SME in fact reproduce the naive schedule because it is the minimal work one. This is what you do when you don't have parallelism to exploit. And we get consistent speed up of about 2 times when input size goes up. Here we have a speed up of 2.39 times. Our next example application is polynomial evaluation. Here's a general degree 6 polynomial. How to evaluate this as fast as possible? The naive algorithm needs 21 multiplication and 6 additions. Again, there are many equivalent ways due to associativity and, in addition, distributivity loss in this problem. Here's the famous Horner's method for evaluating the same polynomial. Horner's method needs 6 FMA instructions, or fuse, multiply, add. This is also the minimum work algorithm. A graphical representation is shown on the right. We can see this is yet again a completely serial schedule. There's no parallelism to be exploited for this schedule. We can do better than Horner if we have instruction level parallelism. Let's say our processor can run 4 FMA or multiplication in parallel. Today's CPU and GPU usually use the same FMA unit for both FMA and multiplication, so we model it as a single kind of resource. On the left, we have Horner's method. As we have noted, this is completely sequential and takes 6 cycles on our processor model. On the right, we have the result from running scheduling modular equality, starting from the Horner's method as an input program. The resulting network now has 8 operations in total, so there's 2 more operations. But the sequential dependency is broken, so that it takes only 3 cycles to run on our processor. So that's 2 times faster, even if it does more work. And here are yet again the measurements on my CPU. From the documentation, this FMA instruction and also the multiplication instruction both have latency of 4 cycles and throughput of 0.5 cycles. And again, that means we can run 8 FMA or multiplication operation in parallel. Because polynomial is a function that takes a single input value x and some constant, we are measuring the latency of this function in terms of cycles. We see that for degree 1 and 2, which is some pretty trivial computation, there isn't a difference between Horner's method and FME. Both reproduce the trivial network, the trivial thing to do it. But for polynomial of higher degrees, SME pays off significantly. Here we see we get 1.68 times shorter latency for degree 8 polynomial. Finally, we have one more measured application for exponential moving average filter. This is the simplest linear filter and is widely used. It is defined by this linear recurrence relation. The output value at index n is the input value multiplied by a, plus the output value at previous index plus the output value at previous index multiplied by 1 minus a, where a is a constant between 0 and 1. The naive implementation runs sequential multiplication and FMA to compute every output sample. We can do better to explore the instruction level parallelism. We first unroll the recurrence relation a few times as shown on the left. We have the computation graph from unrolling 6 times. This takes 12 cycles to process 6 elements, which is as expected, because each element takes 2 cycles to process, 1 for FMA and 1 for multiplication, and this is completely serial. Then on the right, we have the result of applying scheduling modular equality. The schedule on the right only takes 6 cycles on our processor model with a throughput of 1 cycle per element. So this is yet again a theoretically 2 times speed up. We again measure the throughput on my laptop and compare to the naive sequential algorithm. You can see we get a speed up of at most 2.42 times when we have an unroll size of 12. Okay, finally, let's discuss a bit about what we have learned and future work, etc. First, one question you might have is why we are using EGSAT for this, given our work presented in the previous talk. So I think the strength of EGSAT here is optimality. For many examples, we are able to get guaranteed optimal schedule, which is just not possible with, say, a pure stochastic search approach. So we know we have an optimal schedule if EGSAT saturates and if ILP solver terminates with output, quote, optimal. We are able to get such optimal guarantee for most examples in the previous experiment within 5 minutes. Most times are spent in the ILP solver. The EGSAT phase usually takes less than 1 second, and then a few minutes in the ILP solver. Second question you might ask is, how does this scale to, say, hundreds of instructions, like a real instruction scheduler? Can you guess the answer? It does not. But what to the rescue? Stochastic search to the rescue. Some flavor of stochastic search might help. So first, as we observed, we are already spending majority of the time in a complete ILP solver. If you don't care about optimality, we can use an incomplete ILP solving technique, which are usually some flavor of stochastic search or local search. Then we just might go one step further and replace EGSAT with stochastic search as well. So then this whole stuff will be based on stochastic search, but that's future work. Another direction of future work is modular scheduling. Two of our 3 examples involves first unrolling an iterative loop a few times, so we get a computation graph to work on. If you are not familiar with modular scheduling is a cute technique that effectively solves the scheduling problem by unrolling the loop infinite number of times, schedule it, and rolling it back. My co-author Rupanshu and my advisor Alex has a bunch of work on this, so it will be interesting to see how this integrates. Finally, the current examples are all kind of at toy level, right? We need more ideas for application. Tell us about what you have in mind. That's the end of my talk. Let's discuss.
All right, thank you so much. We have plenty of time for questions.
So you mentioned that the ILP solver is actually the bottleneck. So
Yes.
have you considered using a specialized extraction algorithm for your specific problem?
Oh, I haven't, but I think we need to design this so. First, the extraction part is a scheduling problem, right? It's not just a weighted sum of graph node. So we have to think about how to. So there were lots of research on scheduling algorithm that is more scalable than ILP, like usually based on some meta heuristic or local search again. And it will be interesting to see, like, can we extend this to eGraph, because all those previous scheduling algorithms, they work on non-eGraph or RCP, right, or ground terms. So it will be an interesting direction to see, like, can we extend some of this technique to our eGraph? Okay.
So maybe I missed something, but I think my impression is that you're solving this entire thing as one giant ILP. Could there be something potentially that involves pruning of smaller budgets and building like that, or is the problem just not amenable to that kind of an approach?
Oh, right. So in fact, I have some schedule that is less interesting than solving the optimal ILP, but it works pretty well. So there are some heuristics to do it, and I haven't spent enough time on this, but I can tell you that so this schedule, this heuristic, they won't give you the optimal result, but lots of times it can be pretty good. So for example, you can first prune the eGraph, remove all the node. So only retain the node, only retain the node that result in minimal depth. And this is not unique. So for example, Cockstone is a term that give you minimum depth, but it duplicates lots of work. But there are maybe some other terms with depth 3. And now you prune the eGraph that will only retain the minimum depth node, then you do minimum work extraction. So this will give you something better than either minimal depth or either minimal work alone. Because as we see, if you do just minimal depth, this will give you like Cockstone and with lots of duplication. But if you just do minimum work, this will give you the naive schedule, right? This will just straight on give you the naive schedule. So like by doing this two-phase, interleave a bit, I can get a better schedule, like from doing them alone. But this will not be as good as the ILP approach, which will give you the optimal schedule. And I think I haven't thought enough about this. I don't know how to integrate the processor model into this, but there might be a way. But I don't know yet. That's the answer.
In a lot of these problems, have you observed that there's oftentimes like a pretty continuous or like local loss landscape, or does it require like a lot of rewrites and then all of a sudden your latency improves quite a bit?
I don't recall. So first, I don't know what cost landscape really means. I mean, cost landscape is well defined for local search, but here we're doing a like ILP problem. So what does cost?
Well, I mean, as in, if you were to switch to like full stochastic search, it requires many rewrites strung together to actually show an improvement in latency, it would be pretty difficult to do entire stochastic.
Right, that's a very good question, and we don't know yet. We should try.
Really great talk. Have you considered like internalizing searching over all the sequences like into the eGraph rather than the extraction stage? I mean, I know that seems like crazy, but people have been talking about baking associativity in and baking AC in, and there is such a thing as a partially commutative monoid or traces. So there's something that interpolates between the two.
Yeah, or baking scheduling in. Is that what you mean?
Baking scheduling in, indeed. Is that what modular scheduling is? I haven't come across that term before.
Modular scheduling is probably not about it. So
Okay.
it's not directly related to eGraph. But yeah, that's a really good idea, and you should work on this. That's your work. That's your work. That's your work.
Okay, and let's leave it there. Let's thank the speaker one more time.
Thank you.
Looks good. Take it away when you're ready.
Okay. It's really nice to have a chance to talk here and really well organized. The talks are about optimal or whatever things about using ILP for eGraph. And here I'm going to describe how we use answer set programming on eGraph extraction. So I'm the final year PhD student from ELAS group. And after that, we are going to show some more outlook on how things working after that. So start with one single page. We want to extract the best expression or term in the eGraph because there are so many. Let's see, here are 3, and we are going to find the best. By default, is going to be the AST size. So the input of the problem is eGraph, and the definition, then the output is going to be the lowest cost term. So it has been known to be a pretty hard problem. And there have been attempts on using ILP, SAT, and greedy, whatever. So it's very hard, not just the previous slides, they are so simple, but in reality, the graph can be large, and there are loops, there are shared nodes, so overall it's a solver problem. Before going to the solver part, let me first introduce what is happening in the greedy part. So initially, if the node has no dependency, then we know the cost. That's the bottom stuff. And for the remaining thing, the cost of the node is going to be the cost of itself plus the children it is depending and what is being selected. So start from the bottom and trying to go up. So find that x is having the best cost because it's just 1 and the remaining are having 3. In a real case, the greedy search is about to find in each E-class find the best cost on its own without thinking about sharing. That is why DAG cost can sometimes be better than the greedy cost. Let's see, on the left, we are selecting the node of A in the E-class. The total cost is 29 compared to the thing on the right. It's actually selecting the node with cost 9, but it's optimal because there are shared node and 5 is going to be reused twice. All right, that's the problem on sharing, and another problem is on cycles, because if the node you are selecting is having some dependency, you cannot do this because there's no way to extract the final term. Okay, so I guess I won't expect a lot of you know what is answer set programming. So we just introduced what's the problem setting. Now I'm going to give a brief background on what is answer set programming. So everyone should know SAT. SAT is basically find the propositional formulas satisfiability. Let's say we have by implication of A and B. Here in the CNF format is by something, and there's going to be 2 models. The first is both of them are false. The second is going to be both of them are true. And we also have data log. Data log is logic programming way to encode certain reasoning. And we have A if B in the first line and B if A in the second line. The difference is the data log is having the least fixed point computation. So different from the classic implication, there's going to be only a single model which is empty. Basically, both A and B are being false. So you see the difference of implication and the logic rules here. So we're going to show a bit more later on how ASP is going to combine this together. But before that, one of the good things of logic programming is the things can be first ordered. Let's say we have basically here initially we define some facts saying there's an A from A to B and B to A to B and B to C. And initially we also know A is reachable. Then we don't need to specify all of the rules to reason about which later nodes are being reachable. But instead, we have such first order rule saying, okay, if X is reached and there's an age, so we know why it's going to be reached. So after this rules being grounded, is something like that. And finally, we know the model is going to reason that all of the nodes are reachable. And what I didn't say before is, in data log, by default, there's no negation in the body. And negation is really problematic thing in logic programming. Because if you think about the reasoning, you start from the body to the head. If the body are all of the positive literal, the model is going to be grow in a way. Instead of there's going to be negation to disable certain fixed point computation. That's why in the data log, there will be only one list model. But when we have the default negation, there's going to be choice between different models. Initially, we still have nothing in the model because we have A if not B and B if not A. But from the initial point, we can apply not B then A, and also not A then B. So there will be two models, and it's called stable model because after applying them, they are stable. No more thing can be applied. Yeah, that is basically the semantics, very basic semantics of the ASP, although in reality, there are a lot of different extensions from the basic logic programming path. So the high-level intuition about ASP is to generate different possible models and use the constraints, which in the form of rule without head, to eliminate certain models. And potentially, we have some optimization metric to get the optimal models. So it's like starting from things like that and encoding the constraints. And also, we have the max set style stuff. So basically, here we have the choice on A and B. And with eliminating the stable model saying, OK, A and B cannot be both true and both false. So we only have two in the end. Now we start to explore what is happening on ASP for extraction. OK, we are not the first one working on it. Actually, 3 years ago, our superstar Philip used to have a blog post on how to use ASP for EGRAPH extraction. And also, as we mentioned, Remy was also contributing to this. And the idea is to encode all of the EGRAPH facts into logic facts, and then use all of the ASP reasoning to dealing with the extraction. So on the right is the x plus 1 equivalent to y plus x, and it's going to be expressed by logic facts of in nodes, child, and whatever. So that's 3 years ago. Still, bottom up is the initial attempt on how to use ASP, because the mindset is basically we are going to deal with loop. And if we have to eliminate the selection where there's a loop in it, it happened to logic programming happened to express the elimination of the circle, because the first rule here is basically saying we can choose a node if all of the child have been selected. So if there's a loop, we will never reach this point, because the semantics of the head and body is different from logical implication. That's really good insight, and Philip used to have all of this really clean implementation. And it's not working. I want to show a demo. This bottom up is the real code from, OK. So here's a EGRAPH page, 1,000 inode. If just use the default thing, it's going to cost, but it takes very long time. What I did after clone Philip's repository is just to see, OK, how about two-thread? And it's fast as hell. So what is happening right here is really about silver. Even if some expert know ASP a lot, it's hard to know what is happening in the solver. What really makes sense here is there's different optimization strategy. And if we are enabling something called unset core, it's just working. And it's not the default setting of ASP solver. And happens to be the case that the second thread is using that. That's why. So NSAT core is the game changer here. And the main difference is when we have the branch and bound, it's going to search the model in the whole search space and to bound the search. But the core guided search is going to try to have a potential cheap model and then do the NSAT core guided bounding on the max on the optimization solving. And there's some historical reason because, the NSAT part used to be implemented in EGRAPHS. So by default, Klingo is still using the collapse one, which is branch and bound. And that is working very well, but we also want to see what is happening to the top-down one, because the greedy is basically from all of the lifts and to the root. What's happening for the top-down is there's really issue about the loop, because you start from the top and you have to choose it no matter what that is, then it's never going to eliminate the circle. Fortunately, logic programming can express a cyclicity by transitive closure. So the transitive closure is basically having the reachability rules saying, so something can be reachable and the recursion definition on it. But the problem of this method is about when we have the first order program of ASP, it's going to be grounded to propositional ASP. And it's going to be n to third for this. It's not going to be scalable for real EGRAPHS. So it's expensive grounding. What can we do here? It's called ASP modular cyclicity. It's actually some kind of thing similar to SAT versus SMT. But when something is not easy to be expressed in logic programming, you just have the check outside the solving and have the propagator feedback to the ASP solver. And it happened to exist in the Klingo solver without any document. I just happened to find it. I try to implement it, and I remember there's something, and it is working very well. So let's come to the evaluation part. So we have the expression gym suite, having 3 different suites, and 4 configuration. We have the bottom-up and top-down. Also, in the repository, the state of art is the optimized ILP. It's the naive ILP with a lot of pre-optimization or whatever. So our thing, as you can see, is really naive. It's just lines of code without some pre-processing or whatever. And we have 10-second timeout comparing with the 10-second result of greedy. So here's the quality. We overall find really nice number of optimal benchmark compared to, not necessary to be the optimal, but better than greedy compared to the 10-second execution of greedy. And it's better than ILP in general on quality. And the performance is also quite impressive. As you can see, compared with faster ILP, we are still getting better on a lot of cases. And overall, we are much better than the naive ILP. And yeah, that is. And there's some real interesting case study when we try to explore what are the outliers, because as you can see, here the bottom-up one is having better optimal result, but overall it's slower. So here's my personal understanding on what's happening. So these 2 bottom outlier here are having a lot of roots on the EGRAPH. So if you think about how CDCL is working in SAT, it's also happening in ASP. When the root number is being small, starting from the root, you can get a lot of benefit by the CDCL loop. But if the root is containing a lot, starting from root is actually being costly because there are so many roots. But instead, starting from bottom can potentially prune a lot of root in that case. That's why, that's basically my personal understanding on what bottom-up can be better in certain cases. And of course, this makes a lot of sense when you're trying to think about how the EGRAPH expression can work in general. There are so many solvers, And I personally believe that you need to understand what is happening in each property of the eGraph and to see what is going to be the correct solver or correct setting for different eGraphs. Okay, here's the wrap-up of the ESP part. So ESP is powerful, but sometimes it powerfully sucks because the system is too complex. The language is hard to understand, and you need to understand what is solver working and also a lot of different settings. And that says we have quite good initial result on combining, on using ESP for eGraph extraction. What's going to happen next is we want to look at whether it's possible to combine them together, because we know that there's AgLog and ESP is essentially generalizing AgLog, generalizing data log with non-monotonic reasoning. So in the traditional AgLog, it's about we have the saturation, and then we compress by the equality of saturation, and then do the extraction. How about that? We can possibly, okay, here are just about the brainstorm. There's no implementation yet, but I just want to share the idea. ESP is likely to be able to control the saturation instead of, you always do the fixed point computation. But the non-monotonous reasoning part of ESP is possible to prune something earlier instead of you always do the saturation reaching to the fixed point. And the high-level picture here is, okay, we use ESP for defining the search and the efficient search in the CDCL style stuff. And eGraph is essentially compressing the search space. And hopefully there's something happening to, just like what is the previous talk are talking about. There are different ways to do the search, and hopefully ESP can come here to do something. And I want to introduce a bit more on what detail the ESP's features can contribute here. The first is called incremental solving. So incremental solving has been applied a lot in stat solving. Basically, you know the whole search space, but you don't want to search it at once. But instead, you are having some initial result on a subset of the constraint solving. Then after that, you are going to make the search larger by introducing more literal or whatever. And that is quite similar to what is happening in equality saturation, because it's step by step, we keep applying the rules and finally reach something. And the second thing is really about the propagator I mentioned a little bit. Is somehow complex, but the reason I'm mentioning here is I don't think equivalence is very straightforward to be expressed in logical programming. But if there will be a good customized propagator that we can do ESP modulo equivalence, that is potentially the way to combine the things together, and both of them are likely to benefit from each other. Okay, here's the overall takeaway. I personally think that even if the performance is promising, it's still small lessons because extraction is overall just problem never going to be solved very well because it's NP hard. But yeah, we have all of the techniques in ESP, and potentially if we are applying all of this into equality saturation, we want to benefit both of them. Okay, so closing, if you are willing to try more on ESP, you can try Klingo, which is a state-of-the-art system having a lot of interesting features. And if you find it too hard to use, I'm here open for any collaboration on ESP. And we also have designed a new front-end language for ESP, which is going to be released soon, hopefully to improve the user experience of ESP. Okay, that is. Thank you.
Thanks for the talk. We definitely have time for questions. I'll start off with a question. So I'm by no means an ASP expert, but it seems like you were sort of hinting that there's this internal notions of propagators and this graph propagator, and then at some later point you have this ASP plus egg slide where ASP is sort of handling the choice element. Are you sort of picturing congruence closure and, well, maybe what else as a sort of additional propagator, or maybe say a little bit more about how you might split split up those two things?
Yes, so it's really interesting, and also what I'm thinking of, because in AgLog, things are just like fixed point computation, but we have choice here, and potentially if everything in the AgLog can at least be encoded in ASP, and we extend all of the thing to ASP part, I guess the propagator is likely to be the way, because I don't think, in principle, there are better way to extend the basic logic programming method. The propagator in practice is not that straightforward to discover, because you need to find what is the feedback one from the theory. But yeah, for the age, for the cyclicity, it's pretty good.
Okay, so maybe I missed it, but you mentioned faster ILP and ILP, or what's exactly the difference?
So the faster ILP, so the ILP is basically encoding the constraint solving in a file and run it in CBC. And faster is having some pre-processing. Okay, I didn't read every code of that, but I find certain judgment on if there's some node with zero codes, then some elimination or some optimization based on such information. So my personal understanding is, okay, get some very specific optimization and make the overall things faster. I'm not an expert on the ILP part.
I have one more quick question. One of the things that is interesting about the language we use, not only in equality saturation, but compilers and stochastic search, is we say optimization, but really we mean sort of embetterization. Like, we're okay with making things better, and in many cases it is not wrong at all to return a non-optimal result. Sure. And we saw this in some of the previous talks about how if the ILP solver is running in a mode where it can give back a non-optimal answer, things can be much faster. So I guess my question is, what does ASP offer in that regard? Like, can I move towards a potentially better but not known to be optimal solution, and can I use that to make scalability much better?
Yeah, actually I have never think about it, but there are heuristic-based programming in ASP. So I suspect that the heuristic is basically similar to SASOing, but if you have some domain-specific things for the certain class of EGRAPHS, you can always encode them to guide to the solver reaching to suboptimal stuff in a way, collaborating with CDCL. I mean, there's no theoretical result, but there's something in the existing solver.
Okay, cool. Thank you very much. And with that, let's thank the speaker one more time.
Hello, everyone.
It's on.
Okay. Is it better now? Hello, everyone. Can you hear me?
Okay. Yeah.
All right. All right. So, hello, everyone. My name is Akash Pardeshi, and I'm here with Meadows, and today we'll be presenting our work series. So over the over the past years, there have been many popular works using equality saturation in various domains. One of the early applications was Herbie. Herbie is a tool that improves the accuracy of floating point expressions. And more recently, there have been several works like Diospiros, Isaria, and Misal that use equality saturation for compilers. So I'm assuming here that everyone is familiar with equality saturation. I just want to introduce some terms I'll be using. Equality saturation has two phases. There is first the exploration phase where the rewrites are applied. And this exploration phase continues until either saturation is reached or more commonly a resource limit, which typically a node limit is reached. Once the exploration phase is done, that EGRAPH is called the explored EGRAPH, and that's what's passed into the extraction phase. All right. So recent research on equality saturation has greatly improved many aspects. For example, there is egg and egglog, which have made equality saturation fast and extensible. There is ruler and Enumo, which can synthesize rewrite rules so that domain experts don't have to manually develop them. And there is Smoothie, which makes ILP-based extraction much faster and can handle nonlinear cost functions. So despite all these advances, equality saturation still has some limitations, such as its unfavorable memory scalability. To see what I mean, let's go through some of the drawbacks of using a large node limit. The first drawback is increased memory consumption. So we observed that in real equality saturation applications, the exploration phase usually stops due to reaching the node limit and not reaching saturation. And so with a very high node limit, we're basically letting the EGRAPH grow very large, which takes more memory. So as a concrete example, consider Herbie. Internally, Herbie uses equality saturation to generate candidate expressions and then simplify them. So in this plot, the x-axis shows the node limit that we set for the calls to equality saturation inside Herbie. And we go from 8,000 nodes, which is the default that Herbie uses, all the way up to 128,000 nodes. And on the y-axis, we show the bit error of the floating point expression for all the expressions in the Hamming benchmark. So we see that for the default node limit of 8,000, the error is 21 bits, and if you go all the way on the high end to 128,000, the error drops down to 10 bits. And so this is a very significant reduction. And if we take a look at one specific input expression, so here's the input expression, it has 29.9 bits of error. And if we run Herbie with its default 8K node limit, it produces this expression, which basically does nothing and doesn't reduce the error at all. But if we run Herbie with 128,000 node limit, it produces this expression, which actually has almost zero error. So this shows that by using high node limits, Herbie can achieve significantly better application results. But these better application results come at the cost of more memory consumption. So this plot shows that as the node limit increases, the memory consumption grows linearly. And at the highest node limit of 128,000, Herbie is taking more than a gigabyte of memory. And so this high memory consumption is one reason why the Herbie designers decided on such a low node limit of only 8,000. So the high memory consumption we see isn't specific to just Herbie. We see that Misal also regularly takes 1 to 2 gigabytes of memory per benchmark. And Diospiros uses even more memory, up to 35 gigabytes in the worst case. So many applications using equality saturation are facing high memory consumption. And given the tight linear relationship we saw between the node limit and memory consumption, for the rest of this talk, we'll be using the node limit as a proxy for the memory consumption. Okay, so the second drawback is increased rewrite search time. Even the fastest current E-matching algorithm takes time polynomial in the size of the E-graph. So with a larger E-graph, searching for rewrite matches will take longer. And the final drawback is with the extraction phase. As someone mentioned before, extraction is an NP-hard problem, so there are both exact and heuristic methods. And these exact algorithms are based on ILP, which do not scale well to large E-graphs. For example, even with Smoothie, extraction takes around 30 to 40 seconds on relatively moderate size E-graphs with only tens of thousands of nodes. So therefore, using a high node limit comes with several drawbacks affecting the practicality of equality saturation. But we've also seen that applications kind of need to use high node limits to get good results. And so thus, application designers have to make a choice between practicality and getting good results. The solutions to this memory scalability problem kind of center around rewrite scheduling. So a rewrite scheduler controls which rewrites are applied in each iteration of the exploration phase. For example here, a rewrite scheduler would control which rewrites are in the set R1, and then which rewrites are in the set R2, etc. And there are two types of schedulers. First is static scheduling, where the scheduler determines the schedule ahead of time without seeing any specific input expression. So once the scheduler decides on a schedule, it's fixed and will be used for whatever input expression is fed in. So this schedule would be decided ahead of time, and then for any egraph that comes in, you then apply these rewrites to get the egraphs. Examples of static schedulers include simple scheduler, which just applies all rewrites at every iteration, and also Isaria, which consists of 3 phases with different subset of rewrites in each phase. Clearly, static schedulers are limited in the amount of information they have with which to make their scheduling decisions. So the next type of scheduler is a dynamic scheduler. A dynamic scheduler decides its schedule at runtime based on dynamic information. So based on whatever initial egraph it sees, the scheduler can then pick its rewrites R1 and get a new egraph E1. Based on this set of information, the scheduler can then pick its rewrites for the next iteration, etc. So examples of dynamic schedulers include backoff scheduler, which is the default in egg. Backoff scheduler uses an exponential backoff heuristic to temporarily disable rewrites which are matching too often. And of course, this requires tracking how many times each rewrite is applied at runtime, so this is a dynamic property. Another example is MCTS GEB. It uses a Monte Carlo tree search algorithm to decide on what rewrites to apply. And this is also dynamic because to do the tree search, you need to know the egraph, which is only known at runtime. So if you consider this example, this is a very big randomly generated math expression. And if we run equality saturation with simple scheduler, the explored egraph has 6,000 nodes and gets a cost of 3,300. And if we run backoff scheduler on the same expression, for the same number of iterations, it produces a smaller egraph with 5,000 nodes and achieves a lower cost of 3,200. So this shows that backoff scheduler is able to use its dynamic information to make better scheduling decisions and get both a lower cost, which is better quality, and a smaller final egraph, which is less memory consumption. However, current schedulers have a limitation. They focus on controlling the size of the egraph without considering the quality of expressions contained within it. For example, backoff scheduler is explicitly designed to control the size of the egraph by disabling those rewrites which match too often. However, some of those rewrites might be important towards getting high quality, low cost expressions, but backoff would just disable them. So as we've seen with Herbie, which actually uses backoff scheduler, you still need to use high node limits to get good quality. And this affects practicality. So to address this limitation of existing rewrite schedulers, we introduce series. Series is a dynamic rewrite scheduler that biases the exploration phase towards high-quality expressions. It does this by identifying what we call important rewrites. Important rewrites are those rewrites which contribute towards the search for high-quality expressions. And redundant rewrites are the rewrites that do not contribute towards this search. So series enables memory scalable equality saturation. It ensures that the eGraph never exceeds a specified size and a specified node limit. And under this node limit, series can find equal or better quality expressions than is possible with current rewrite schedulers. And so this allows series to go with a much smaller node limit, which is in the region of practical memory consumption, while still getting equal or better results. And second, series is portable to many diverse equality saturation applications. Later in this talk, we'll show our evaluation results on 3 different applications. So first, I want to give some intuition behind what important rewrites are. So consider this eGraph and these 2 rewrites. If we apply the rewrites, we get this eGraph, and the root E class represents these 2 expressions. So the first expression has cost 5, and the second one has cost 6. So we might be tempted to say that the first rewrite was more important since it brought down the cost. But if we keep rewriting, we would find that the first expression's cost doesn't go down, but the second one goes all the way down to 4, which is that optimal expression from earlier. And so therefore, we say that the first rewrite is redundant, and the second one is important for this specific eGraph. Okay. So there are challenges to this approach of deciding on important rewrites. So I said earlier that an important rewrite is one that contributes towards the search for high-quality expressions. The problem is, we don't know beforehand whether an expression is high quality or not. And furthermore, with current rewrite schedulers, that most optimal low-cost expression might be out of reach within the node limit. Second, we cannot test rewrites for importance independently. It's very common that multiple rewrites might need to be applied in a single iteration for subsequent rewrites to be applied in later iterations to get towards that best expression. And so this means that if we can't test rewrites independently, we have to test subsets of rewrites together. But that means if there are n rewrites, then there are 2 to the n subsets. And given that real eGraph applications have hundreds or thousands of rewrites, you can't. That's just intractable to search overall combinations. And finally, the set of important rewrites is a dynamic property of an eGraph, which means that if we can somehow find what this set of important rewrites is for one eGraph, then later on when we have another eGraph, we're going to have to do this search again to find the set of important rewrites for that eGraph. All right. So now let's talk about how we formally define what the set of important eGraphs is for a given, the set of important rewrites is for a given eGraph. So I said that we need to test subsets of rewrites. So we want to find some subset Ri that minimizes some objective function. So what should this objective function be? Well, one natural thing we can do is for the subset Ri in question, we can take our initial eGraph, we can apply that subset for one iteration, and then apply all rewrites until reaching either saturation or the node limit. And that tells us 2 things. So first, from that final eGraph, we can get the cost of the extracted expression. And second, we can also check, we can get the size of the eGraph in which that expression first appeared. So now this is our final objective function, and it has 2 pieces. It says that we want to get low cost, and we also want the eGraph to not explode. So note that we can reduce the size of the search space by only considering rewrites which match in the eGraph. Any rewrite which doesn't match isn't going to affect this cost function. Here we have the distribution of how many rewrites match. This is for Herbie. So one thing to note is that out of the 200 rewrites for Herbie, there's never more than 100 matching rewrites, so that already cuts down the size. Obviously, 100 matching rewrites is still too big. The other important thing to notice is that 20% of the time, there are actually 5 or fewer matching rewrites, and 5 is small enough that you can just exhaustively try all 32 combinations. But for most of the time, the combinatorial optimization problem is too big for exhaustive search. So what can we do instead? We can use the cross-entropy method. So the cross-entropy method is an established technique for finding solutions to combinatorial optimization problems. And the algorithm goes like this. We start with all the rewrites which match, and we give each of them an initial probability of 0.5. We don't know if they're important or not important at the start. From this distribution, we then take n samples, where each sample is a subset of rewrites sampled according to that probability distribution. We then sort these samples based on how well they do according to the objective function. And we kind of take the best samples that we've seen. We look at which rewrites are in those best performing samples and use that to update the probabilities. So now we have new probability distribution, and we repeat the process. We take new samples, again sort them, take the best samples, update the probabilities again. And after some iterations, we'll end up with a kind of distribution that is clearly divided into some rewrites that have probabilities close to 1 and some probabilities close to 0. And so the important rewrites are those rewrites which end up with high probabilities. All right, so now I'll pass it to Devansh.
Hi. So now onto some concrete statistics on the statistics that we collected when we were evaluating series against existing schedulers. So since again, series is specifically designed to address memory scalability, we essentially had 2 hypotheses and we want to test them. The first one, that series can achieve better expression quality given a fixed memory budget. And as a corollary, that it requires lower memory budget to reach similar expression quality. Our evaluation will go over 3 different applications. We will start with a test application of math, which with node limit as 5K. Then we'll move to a popular application of Herbie, with node limits going from 4K to 96K. And then eventually we will look at a compiler application of DSP vectorization called DSP, which has node limits as high as 20 million, which often requires a server machine to kind of meet its memory demands. So math is effectively a simple algebra language, and it has been used in prior works like MCTS as well for evaluations. So similar to MCTS, we kind of randomly generate 50 expressions and evaluate on that. We aim to analyze 2 key metrics, one being the expression cost, and the second relative to the baseline, which is the backoff scheduler, and the second metric being the relative size of the final E-graph. A good scheduler should ideally lie in the bottom left quadrant, since that implies smaller final E-graphs and lower expression cost. So prior work, MCTS, the scatter plot of it does show that it does achieve lower cost at some points, but it also has cases where it does have worse cost. And consistently, it has larger E-graph sizes than backoff. Series, on the other hand, is consistently in the bottom left quadrant, and we almost always achieve lower cost and smaller E-graphs compared to backoff. So that's the first positive result. Now let's consider Herbie, which is again has been commonly used in a lot of evaluations like egglog, ruler, and NEMO papers. So yeah, Herbie uses backoff scheduler under 8K node limit, and that's its default scheduler. And to the best of our knowledge, we couldn't find any prior works similar to MCTS which have been tuned for Herbie. So our evaluations kind of restrict to backoff and series. We select the Hamming problem set, which effectively has around 800 equality saturation calls, and these are E-graphs we evaluate on. Again, to show versatility, we consider 2 rule sets. One being the main Herbie rule set from the Herbie repository, which consists of 200 expert written RIA tools, and another around 300 RIA tools which were synthesized using NEMO. Right. So again, looking at the main rule set, over here we plot the relative expression cost, geomeaned over all the 800-ish E-graphs in the y-axis against the node limit that we set for the engine in the x-axis. As we increase the node limit, we see that the relative cost decrease for backoff, and again, lower is better since we want to have lower cost, which is better expression quality. When we look at series for similar node limits, we kind of observed even lower costs. So at around 8K, series achieved around 20% lower cost than backoff, and the improvement got better, and around at 64K it was 33%. And overall it kind of takes around, so it takes 96K node limit for backoff to achieve similar expression quality as what series can do at just 8K. So overall we achieve like close to, you require 12x lower memory budget to kind of reach similar expression quality. We repeated the same experiment for NUMO synthesized rule set, and similar to last time, backoff also was tapering out around 20% reduction at around 96K. And however, this time series had even lower costs, reaching up to 80% reduction. We believe this is primarily due to that the synthesized rule set includes several rewrite rules that often cause explosive EGRAPH growth. And since series is intelligently turning off redundant rewrites, it allows us to explore to larger depths and find even better expressions. And even at like 12 times lower memory budget, which is like series at 8K, it can achieve better expression quality than backoff at 96K. So, and also series essentially has more benefits, especially when you're using a synthesized rule sets, which are more prone to having such explosive EGRAPH growth. Finally, we have the evaluation on DSPROS, which is a compiler application for DSP vectorization. The developers for DSPROS preferred to use 10 million as the node limit, which when they were benchmarking the 21 DSP kernels. So we again do a similar experiment as Herbie, though this time the default is backoff 10 million. And we see that when we do pick smaller node limits like 10K or even 100K, it does lead to higher expression cost, which does justify developers' choice of using 10 million as the default node limit. On the other hand, series can match or even beat the baseline with just 20K node limit. So series at 20K is effectively 60% lower cost than backoff at 20K, and it has similar geomean statistics as 500K node limit for backoff. We did another analysis on, again, DSP kernels, but this time plotting them with the x-axis being the problem size or the EGRAPH size for individual DSP kernels, and the y-axis being the node limit needed to reach cost convergence. So we saw that we need 2 million node limit to achieve good quality expression for all DSP kernels when you are using backoff. For series, we were able to do the same and reach good quality expressions at just 20K for all DSP kernels. So around 100x lower memory budget is needed for the developers when they want to benchmark these DSP kernels. In summary, we kind of validate our two hypotheses that series achieves better expression quality given a fixed memory budget, and it can achieve similar expression quality at a much lower memory budget. Overall, we presented series, a new dynamic rewrite scheduler, which enables memory scalable equality saturation by identifying the set of important rewrites to be applied per iteration. Thank you.
Thank you to you both. We have time for a couple questions before we head off to break.
Great talk. So I have a few questions. So first, it seems besides important rewrites, you can, like different E-nodes also have a different importance, right? Have you considered, say, important E-nodes or E-classes?
So typically in EGRAPHS, you don't delete E-nodes or E-classes once they are added, and typically the way to control whether they should be added or not is by enabling or disabling rewrites. So that's what we effectively, so we control not adding those, maybe say redundant E-nodes by not allowing those rewrites to run for that particular
I'm thinking of the scenario where, for example, some E-classes are like deep in the past. So even if you over-optimize these, they are not likely to produce a better overall optimal program.
So usually, so usually those E-nodes or E-classes will typically either not be generated when we are in the prior iterations, because currently when we are running equality saturation, it will just apply all rewrites, so those EGRAPHS and E-nodes may be generated. But because series is being applied from iteration 0, those E-nodes and E-classes, if they are not making the overall cost better, they will not be generated in the process.
Okay. Sorry, just another quick question. So could you talk a little bit about the runtime overhead of the cross-entropy method?
Right. So looking at the same node limit, certainly series is slower than backoff because backoff doesn't have to make any decision. But when we do compare at similar expression quality, so when we look at backoff for 10 million in day zeros, that's actually 3 times slower than series at 20K. Because again, smaller node limit, the search time, the extraction time, all of those times are much slower because it's like almost 100, 200x memory reduction.
Just to riff on Yihong's question a little bit, I think one thing that we might be seeing here is a deficiency in the egg API or the egg way of doing things. I think maybe Yihong was suggesting or pointing at a rewrite scheduler that not only turns rewrites off and on, but localizes them in some way, saying like, okay, let's apply this rewrite to this part of the eGraph, but not this other part.
Yeah, so that's also one thing we were considering before. Instead of doing things at the granularity of individual rewrites, potentially you could do things on specific rewrite matches. Like that's still something that's under the control of the scheduler. The scheduler doesn't have to apply all the matches for a rewrite. Yeah, so that's something we will look into in the future.
Yeah. So I just pulled like the latest master, the main branch of Herbie, and it does actually find the log1p 1/n rewrite. So I'm not sure. This might the rewrite set has changed a lot in Herbie, so we might have just added this rewrite recently that causes it to find the rewrite. No. So has Herbie become better? Is that the reason? Yeah. Just pointing it out.
Yeah, so I think the rewrite set that we were using might be a bit old. It's kind of at the same timeline as NUMO, which is a couple of years ago. So the main rewrite set we are using is not. And also, the same issue was also coming with the NUMO synthesized rewrite, where some expressions were, again, log1p is one example, but there was the kind of trend was still visible in like different rewrites as well.
Yeah, I also want to point out for the log_p example, so yeah, it is true that we were using the rule sets that NUMO used in their evaluation, so we could have fair comparison. For the specific log example that I pointed out where it goes from 29 to 0, that was using the NUMO synthesized rule set, so not the Herbie developer one. I would expect that the Herbie developers take this into account and have rewrites for it.
Okay, let's thank our speakers one more time.
Oh, sorry.
About eStitch, top-down library learning for eGraphs, and this is some work that I did with my colleague Maddie Bowers and our advisor Armando Soler-Lezama. And to get started, what is library learning? So the idea here is that code is often quite repetitive, and we can find common structure within it and write a library function that kind of generalizes out that common structure. This is a very common problem that shows up in a variety of different programming languages tasks. For example, program synthesis, you might want to have a shorter overall program that you're trying to generate, and library functions help shorten it, which is helpful. You might want to clean up some code that was written by humans and make it smaller so that it satisfies the don't repeat yourself principle, etc. You might want to discover concepts. For example, if these programs are coming from some kind of a symbolic regression on data or something like that, it might be an important part of your process. And of course, it's useful in a variety of compiler tasks. For example, in decompilation, you might want to be able to pull out library functions from assembly code. And here, we're looking at one particular abstraction, and this represents regular polygons. That's what's going on in the background. And if we rewrite the corpus here to use this library of one function, we end up with a much smaller corpus that is potentially easier to understand if you were to translate these all into human-readable tokens. And so, in general, library learning is the process of starting with some corpus. Here, we've got these two programs, and you've got some common structure. And you have that this structure matches at a particular set of locations in the corpus. So here, for example, the common structure is this +2 square root thing, where the square root has some variable, and that variable is unique to each location. And we can rewrite this, so each location gets rewritten to a function call. And this results in the corpus being overall smaller, which is our goal. There's two important pieces of prior work in this space. One of them is Stitch, which is a top-down branch and bound algorithm that is very fast, and it finds these abstractions quickly. But it can't handle rewrites. So it can't handle, plus AB is the same as plus BA. It operates over program trees and doesn't really take into account saturation, equality saturation. Babel, on the other hand, is the other important piece of prior work, and it is useful in that it is eGraph native. So it works by anti-unifying pairs of E-classes together, and as a result, it handles rewrites very easily. However, it's a bit slow. It has a quadratic complexity, and so it's taking minutes on kind of mid-sized problems that Stitch would be able to solve quite quickly, even though it's solving them incompletely. So our question here is, what if we did Stitch, but over eGraphs, right? So then we get the best of both worlds. So just as a quick outline of this talk, first we're going to have our problem statement, then we'll talk about Stitch, then our approach, and then some experimental results. So the formal problem statement here is that we want to find some abstraction f that compresses the corpus p. And effectively, the cost function that we're trying to minimize here is the size of the rewritten corpus plus the size of the abstraction. We add in the size of the abstraction, otherwise the most compressive abstraction would just be the min term of the entire corpus, and then that's just like one big abstraction. Obviously, we don't want that. And so the overall number that we're actually going to report most of the time is the original cost of the overall corpus divided by our cost function. So effectively, if you start out with 100 tokens and you end up with 50, that's a compression of 2x. That's kind of a more interpretable metric. And so now that brings us to the most important piece of prior work, Stitch. Stitch is a top-down search. So you start out with something that matches everywhere, and you make it more and more specific over time. Specifically here, we're looking at this expansion where we look at, okay, we've got something that's a plus and then it matches at 2 different locations, right? So this matches at a variety of locations in the corpus, these 5 specifically. We can do stuff like freeze and say that, okay, this left variable, that'll just stay a variable. We can also expand even in subterms. So here we're saying that the right side has to be something multiplied by something, and again, it matches at the same set of locations in the corpus in this particular case. We can continue to expand. Some of our expansions expand our abstraction without actually making it bigger. So in this case, it's putting in a 2 for that leaf on the left of the times, and that expands how much we're explaining about the corpus at each match location, but it's not actually increasing the size of the abstraction. And here again, it keeps the same set of match locations. And we can finally get a completed abstraction by freezing the last variable, and we end up with something here that actually does compress the corpus. So the original size of the corpus was 35, but if you rewrite using this, it brings the size down to 25. And if you add back in the abstraction cost, that only brings us back up to 30. So we've successfully compressed the corpus at least somewhat. Now, of course, I just showed you the path to the optimum, but there's many other paths you could take. So from this second one, we could instead expand the left side and say, oh, that's a 2. And that would only match at 1 location, but we can continue from here, and we can continue expanding. But wait, is this search path even fruitful at all? Well, one thing we can notice is that at any future point, we only have this 1 match location, or potentially fewer, right? As you expand out your abstraction, you can never gain more match locations because you're just making your filter of what locations apply more and more specific. And at this match location, we can only save 5 nodes because the match location only has 5 nodes in it. So the lower bound on the cost of the rewritten corpus at this search path is in fact 30, right? So it's 35 minus 5 that we could take out, 30. So we can just prune this entire search path because no matter what, we'll never find anything better than what we've already found. And in general, the lower bound here is just the corpus size minus the size at each match location of the tree at that location. And in general, what we find is that lower bound means aggressive pruning. So this is the secret sauce that makes Stitch work, but there is a problem with Stitch. The main problem is that matching is purely syntactic. So let's take that corpus we had before that was very nicely structured, you might have noticed everything matched, and make it a little bit less nice. Let's commute some parts of this corpus, right? So we're going to commute these plus nodes, and we're going to commute these times nodes, or this 1 times node. And this is, of course, equivalent semantically to the original 1 under some very simple set of DSRs. And however, when we run Stitch, exactly the same process as before. It starts out all the same, but then when we try to expand to a times on the right child, we end up with only 3 matches instead of 5. And then when we expand to a 2 on the left child of the times, we end up with only 2 matches. And when we eventually get our final abstraction, the overall cost ends up being 36, higher than what we started with. So not only did we not find 3 of these matches, this entire abstraction will just not be found, despite the corpus being semantically equivalent to the one we started with. So this is obviously a significant limitation of this approach. So that brings us to our approach, which is effectively just running the same kind of a Stitch top-down algorithm, but over EGRAPHS and all the complications that arise when you try to do that. I'm not going to go over a very complicated big picture of this because you've just seen the algorithm. It's more or less the same approach, except when we run into, obviously, an E-class that has multiple E-nodes in it, because then you can match in multiple ways. So effectively here, take this E-class, which has 2 different plus nodes because it's commutative. And the 2 children are square root of something and 2. And when we apply our expansion to this, we match in 2 different ways, right? We can match in one way where the left child of the plus is the left child in the original corpus, the square root, and the right child is 2. And we can also apply in the opposite way, where the left child is the 2 and the right child is the square root. Now, I've shown 2 copies of the eGraph here, but crucially, we're not actually duplicating anything. We've just got these 2 different matches that we're tracking. And in fact, we're not tracking them for very long. If we freeze the left child of our abstraction to 2, we immediately drop one of these matches. So we don't actually have to keep this bookkeeping for very long. And once we eventually freeze that last variable and expand it all out, we end up matching at this particular node, which in the original corpus would have been in the opposite order. So original Stitch would not have caught it. And one thing to note is that we never had to think about the fact that this lower this lower E-class had two different ways of matching. So this is what allows us to handle cycles and stuff pretty natively. We only have to care about the actual multiple matches at the locations that are variables within our pattern. And one other thing, I'm not getting into the details here, it's a little technical, but we also do try to make all of our matches kind of Cartesian. So if there's multiple different variables that could match in different ways, but that are kind of orthogonal, we don't actually store the entire list of possible ways to match. So yeah, there's several interesting to me, things that we did to try to make this work over EGRAPHS. Stitch doesn't just work out of the box, but I was told that they are only interesting to me. So I'm going to talk about one thing here, which I think should be interesting to everyone, which is a better lower bound. So I was emphasizing how amazing the Stitch lower bound is, but it doesn't really work for EGRAPHS. It works well on corpuses, and you can kind of think of it as like the average size of a match times the number of matches. And really the benefit comes from the fact that if you don't have very many matches, you have a very bad lower bound, right? So that's what you're subtracting out, so you end up with not that much savings. The issue here is that on EGRAPHS, there's a huge number of complications that arise. First of all, you can have multiple matches at the same E-class, as we showed earlier. So if you've got multiple matches at the same E-class of your pattern, then how do you handle that? Now, there you could say, okay, well, just take kind of the minimum lower bound over the different ways you could match at a given location. The other problem is that you could have E-classes that appear multiple times in the minimal term, and you're matching at those locations. So how do you handle that? Again, you can generally handle this with a bit of bookkeeping. However, the real thing that will bite you is that some E-classes might appear nowhere in the minimal term because they're just not optimal for that particular location. And if you've got a match there, it might not appear anywhere in the original term originally, but then when you compress it, it might start appearing in the original term. So you kind of need to handle all of that kind of dynamism. So that brings us to our better lower bound. For this, we're going to go over a simple example. So the idea here is that we've got some root node f, and it's got two children, and these E-classes have the minimal term f of this G term and then the H term. Those are the minimal terms for each of those individual E-classes. And then we've also got this much heavier plus term here. What we've got is a pattern that matches at these subnodes of that plus term. And it's completely useless. There's no situation in which this will ever be compressive because it's already frozen the 1 and the 2. So it'll just never be able to do any significant compression on these particular locations. The Stitch lower bound would start by saying, okay, well, each of these subterms where it's matching costs 4. So we could save up to 4 at each location. Therefore, the lower bound is 7 minus 8, because of each of the 4s, is -1. Now, -1 is not a particularly tight bound on the overall cost of this particular rewritten corpus, right? So what we would really like to do is something that's a little bit tighter of a bound. Now, one thing we can do is just say, well, what if we just did the same thing, but we actually took it into account the fact that we're in an E-graph? So we replace the roots with 0. It's basically the same thing. But instead of just assuming that that's going to linearly reduce our cost, we do a bottom-up traversal and recost each of the nodes. So we can then say that these E-classes above are 2, and then the ones above that are 5, or the one above that is 5. And you might recognize this as just the normal computation for the size of the minimal term on an E-graph. And we get the much more reasonable lower bound of 5. The thing is, once we're doing all this work, we might as well do something a little bit more sophisticated, which is to note that we're not actually ever going to be able to rewrite a particular node to 0 cost, right? First of all, the actual function call has some cost, right? You need to put the function symbol in. But then also, we've committed to not expanding the 0 and 1. So those inputs will just have to be inlined in there, right? So we've got this fn1, 2 on the left child, and we've got this fnab on the right child, and potentially more variables, but we don't know those yet. So we'll approximate this, or sorry, not approximate, we'll lower bound this with a 3 at each location. And then if we bubble this same thing up, we end up with a lower bound of 7, which is exactly what the corpus cost originally. So in fact, this new bound realizes that our abstraction and any follow-up abstractions, any expansions of it, are totally useless. So we can prune this tree. And this is true even if we didn't have anything to compare it to. So you might have been thinking, okay, well, this has some advantages, but it seems a little complicated. The advantages are, of course, that it's far tighter than the stitch lower bound. And the other one is that it quickly grows as we freeze variables. These are both advantages that apply even in the situation where you don't have an EGRAPH and we're just operating over a tree. However, there is one significant disadvantage, which is that it's way more expensive to compute. And we'll get into some of that when I get into the results. And now for some algorithms. So how do we actually do this top-down search? One algorithm, this is kind of similar to Stitch, is that we maintain a frontier of nodes that are all, each node is one of these abstractions, and we just pick the best node at every time. We score it based on the cost so far, and we expand it. And this is eventually exhaustive, so it will find the optimum eventually if you run it for long enough. And the main downside to it is that symmetries mean redundant paths. In other words, if you've got like a plus AB pattern somewhere and you've got a plus BA pattern, then you're going to have to explore both of them to some degree. Maybe you'll be able to prune one with a lower bound, but if you can't, you just kind of have to like look at both of these and they're kind of redundant. On the other hand, we also use sequential Monte Carlo, and here we keep a set of particles. Each particle corresponds to one of the abstractions, and you expand each one randomly, and then you reweight them based on the cost. Now, the main downside to this approach is that it's non-exhaustive. Technically, of course, sequential Monte Carlo is exhaustive if you have an infinite number of particles, but my computer is finite. The main benefit, though, is that it is completely insensitive to symmetries. So if you've got a plus BA and you've got a plus AB pattern, and you're evolving them over time, you just have both. And it's not a big deal, because they're just both weighted equally as particles within your search. And you might just pick one or the other, and it doesn't matter. So just to get into what sequential Monte Carlo is to some degree, we start with some particles. Each of these represents an abstraction. We expand it. That's one of those expansions we saw earlier. You then reweight these particles based on the cost function, and you divide that by some temperature. You take the exponent of it. And then you resample the particles, and then you, of course, repeat this process over and over again until you find something good. And now, finally, for some experimental results. Now, I've been talking this entire time, of course, about the need to run these algorithms over EGRAPHS, but you can run these over EGRAPHS that just don't have any rewrite rules in them. So that effectively, this is a comparison on what they do in program trees. And what you find here is that we compare it to both Babel and Stitch. Babel doesn't do particularly well here. It's not really what it's intended for. But you can see that Stitch gets optimal performance, kind of by construction, and so do we. We get kind of very similar performance. And in terms of time, we only have an overhead of about 2x. So that's all the eGraph tracking and everything like that. Doesn't add all that much to the cost of the search. And we're even a little bit better than Stitch on a couple domains that have a very large number of nodes in them. So that's the first two domains. That's because of our lower bound being a little bit stronger than Stitch's, even though it's a little slower to compute. Now, of course, primarily we're interested in domains that do have rewrites. Stitch drops out here because it just can't handle them. And our comparison is mainly to Babel. And in our comparison with Babel, we find that we're able to improve compression a little bit. So we go from 4.06 on Babel, we're able to get 4.85 on average across these domains. But more importantly, the time reduces considerably. So Babel takes about a minute on average across these domains, and we're able to do it in 2.6 seconds. And however, these rewrites, which are the ones from the original Babel evaluation, are not as powerful as we'd like, and we have some other ones that are potentially a better direct comparison between our technique. So that brings us to this new molecule benchmark. The idea here is that molecules are often trees. So for example, alcohols are often trees. And they can be represented as programs, right? They're graphs, but they're tree-structured graphs. One thing about this, though, is that they're undirected graphs. And there's multiple isomorphic representations as programs of these graphs. And so we want to be able to handle kind of extraction of features on these. And molecules in a family have some common structure associated with them. And we want to be able to find that. Now, of course, chemists have solved this problem. They've solved it with this very complicated system of very specific ways of writing molecules down. Effectively, you can think about it as a kind of canonical graph representation. It's called SMILES. But what we would like to do is be able to get the same kind of compression and the same structure finding without any domain-specific knowledge. All we're putting into this is the fact that there are symmetries among and tree rotations and stuff like that, like basic stuff that anyone would know. And the baseline here is, in effect, Stitch applied to the EGRAPHS min term. We're doing this because throwing stuff into an EGRAPH and finding the minimal term itself does canonicalization for you. So we just want to make sure that we're actually getting advantage from searching over an EGRAPH rather than just from the EGRAPH existing in the first place. So that leads us to our molecule results. What we find here is that, first of all, this BFS at start baseline is what I was just mentioning. And in general, it does not do as well. It only gets about 3.6, whereas we're able to get something like 4.7 to 4.8. So we're able to get significantly more structure. And the other thing that's probably that's important to note is that we still produce a strong improvement over Babel, which takes much longer and in some cases runs out of memory before being able to solve this problem. Another thing to note here, and I should have put this on the slide, but another thing to note here is that in the previous examples you might have been wondering, why even bring up the sequential Monte Carlo algorithm? It's not the optimal one. And here you can see why. It's actually much more helpful when the rewrites are more powerful. It's able to find better compression in less time than the exhaustive search. And just for some interesting, pretty pictures here, what you can see is that on one of these examples, we're able to find up here this abstraction that kind of represents this molecular structure that just was not able to be found by the algorithm that's just running a regular search over the minimal term. And some other ones here. I can go back to these later if you'd like. And yeah, so in summary, we've got a couple things that we left out of this presentation. So we handled the Brown indices specially. We adapt a bunch of the pruning rules from Stitch. And we prove the soundness and completeness of our technique. None of that was in this presentation, but it all exists. We also have a few questions for you. One of them was, we represent ways of matching as a Cartesian product over variables. I don't know if anyone here is working on something relevant or knows of anything relevant there, but that seemed like something that improved things a lot in some cases. And the other thing is, do any of you think that there are any benchmarks that would benefit from more scalable eGraph abstraction discovery? And yeah, I'll just leave the summary on here while we take some questions.
Okay, thank you very much. We have time for a question or two.
Okay, so it looks like a Stitch is a kind of greedy process. You extract one abstraction at one time, and then you extract the next. So is there a phase ordering problem here, or there isn't? So
there is, yes.
Okay.
We're not currently treating that as in scope, but I think that our stochastic approach probably would be able to solve this if you then layered on top of beam search, or if you then layered on top of it just more sequential Monte Carlo.
Thank you.
Okay.
Yep.
Then we'll leave it there. Thank you so much.
I'm asking, so someone please take the photo of me to present this, because I was told to do so from the PR team of my company. So yeah, thank you, and you can just share it in the photos channel. Okay. So hello, I am Hiromi Ishii from JIJ Inc., and today I will talk about some applications of EGRAPHS to mathematical optimization. So this talk introduces two applications of EGRAPHS to mathematical optimization. The first is resugaring expressions involving higher order functions into comprehension syntax for LaTeX rendering. And second is more declarative constraint detection, which continues the talk from the last year's workshop. And the first topic also turns out to be important for the second one to achieve practical performance. And through these examples, I want to share two general lessons for writing EGRAPHS rules. First, Hanking constant-like trick is useful for propagating facts while substituting bound variables. And second, and most important thing, is that you must optimize or decompose the premises of EGRAPHS rules. Otherwise, EGRAPHS may not even reach equality saturation. Okay, and overall, equality saturation and database-backed logic programming fit mathematical optimization surprisingly well. Okay, here is the overview of this talk, and first start with the overview. So, what's JIJ modeling? So, JIJ modeling is a modular Python EDSL for mathematical optimization. So, what is mathematical optimization? Luckily, we have some talks about mathematical optimization, so we can just see this quickly. So a mathematical optimization problem asks to decide variables to minimize or maximize an objective function subject to equality or inequality constraints. So a typical example is knapsack problem. Yes, and in this formulation, W, N, Vi, Wi all input from users and determined by the real-world settings, and Xi's decision variables that is determined by the solvers. Okay. So JIJ modeling is a general-purpose mathematical optimization modular implemented as a Python EDSL in Rust, and it compiles a high-level problem formulation into the solver-agnostic Omix format and passes to the solver. And its distinctive feature is to utilize separates the model definition from the input data and utilizes the information of abstract syntax tree as far as possible. And here is the example formulation of knapsack problem in our JIJ modeling, and on the left is the formulation code, and on the right is the mathematical output that is automatically generated from the left. Yeah. So, and JIJ modeling too is can be viewed as a total programming language based on simply typed lambda calculus. And in applications, we do not need full alpha or beta equivalence, although some limited forms of substitutions needed in the second application. And this is because we treat formal transformation and queries on expressions, but not optimizing the variation of the program. Okay, so as promised, the rest of the talk has two main topics. Both topics rely on the formal AST information and on the powerful inference mechanism provided by EGRAPHS. Okay, so let's go on to the first topic, comprehension refiguring in math output. So as a background, we first discussed the treatment of summation symbols or bound variables in JIJ modeling 1 and 2. Previously, users had to create an artificial element object, I here, and together with its domain N here, and this kind of artificial syntax is really unpopular, so we introduce higher order functions such as map, filter, or flat map so that subscripts can now be represented as bound variables. And we also introduced the Python decorators that allow users to write those expressions using comprehension syntax like this. And under the hood, it produces function source code and the symbolic transformation on ASD. So when we process comprehension syntax, we describe it using flat map, and filter as in the standard transformation. So this gets like this. This is fine as internal representation, but if we translate it literally to mathematical output, the result is not human readable. So the challenge is, how can we convert equations involving higher order functions back into human readable mathematical equations? So we consider resugaring here. So we regard mathematical output as a program transformation and consider resugaring the comprehensions. There are two layers of the rules here. So the first layer transforms expressions into comprehensions, so these rules. And under the hood, it calls the second transformation to resugar membership relations into the right-hand side of comprehension syntax. And throughout the transformation, we bind fresh variables for each for class and to avoid name collisions. This already gives much better result, but still not human readable. So there are so many bindings like this or like this, and so we want to reduce such rebindings, and to overcome this, we introduced another optimization path to reduce unnecessary bindings, and of course we used EGRAPHS here. And on the right is the excerpt from the rules, and the equality saturation and extraction feature helped us a lot. And rule set feature also let us flexible control over execution order. As an outline, we assign high cost to let expressions so that expressions avoid unnecessary bindings, and we also assign lower cost to the variables bound later in right-hand side because it is more likely to appear in the left-hand side. And we union both sides of let statements, and when the left-hand side of comprehension is a single variable, we unload its definitions. And with these rules, the mathematical output becomes much more concise and close to what human would write. Okay, so in summary, GHG modeling provides powerful mathematical output, but higher order functions make the direct output less readable after comprehension desugaring. The solution is to pass resugar back into the comprehension syntax while rebinding everything to avoid name collisions. Then we apply an optimization path to reduce rebindings. And in most cases, this finishes within 100 milliseconds. So we treated mathematical output as program transformation plus optimization, and as a bonus, even programs originally written directly with filter or map or flat map can also be displayed as clean mathematical notation. And we also register type information of subterms into EGRAPHS database and use them to fine control the rendering. So that database feature really helps us a lot here. Okay, so next we move to the second topic, declarative constraint detection with EGRAPHS. Okay, so this topic is a continuation of last year's talk. In mathematical optimization, some specific kinds of constraints can be exploited to speed up solving. Examples include SOS 1, 2, and 1 hot constraints. And some solvers provide dedicated APIs for such type of constraints. However, users are not necessarily a mathematical optimization expert and may not know that their formulation contains such useful constraints. So it is therefore valuable if the modeler can detect them automatically, and this is what GHG modeling is able to do thanks to the model data separation. So as an example, An SOS1 constraint is a constraint over a family of non-negative variables, xi's here, that demands the at most one variable is non-zero. And users write such rules using equations rather than symbolic, this is SOS1. So if all variables are binary, it can be written as just their sums are at most one. And for general non-negative variables, not necessarily binaries, we can express it as like this, with fresh auxiliary binary variable delta i's, and each upper bound of each xi's mi, and we express this as a SOS1 on deltas and this kind of upper bound constraint. So, and if we want to detect general non-negative variable, SOS1 general non-negatives, so this kind of multi-step rules, GIG modeling 1 needed to do back and forth between egg and last, and we also didn't make use of extraction features there. In contrast, in GIG modeling 2, EGROG's logic programming paradigm allows us to do this completely inside EGLOG, and we can also use generalized extraction or querying feature to extract a term representing the domain of detected SOS1 constraint. Okay, so there are two main challenges. The first, we want to detect equivalent patterns all at once. For example, we want to detect both of these. These are algebraically equivalent, of course. So by a single pattern, and of course, equality saturation is a natural tool for this, and GIG modeling 1 uses egg, and new version uses EGLOG. And the second challenge is more subtle. How do we handle instantiations of bound variables correctly? For example, to detect SOS1 constraint over general non-negatives from conditions like constraints like this, so we must combine information from the constraint on binary variables here on even i's and upper bound constraints, parameterized upper bound constraints. And GIG modeling 1 used ad hoc trick. It requires upper bound constraint to have exactly the same subscripts as binary SOS1s with possibly wider domain. But GIG modeling 2 now abolishes element object and switch to higher order functions. So the GIG modeling 1 trick just works because there are element type and the elements are fixed globally through the, that somehow works. So we have to devise a new trick to overcome this. And this led us to a trick inspired by Henkin constants, which propagates paths without proper built-in support for bound variables and substitutions in the EGLOG. Okay, so what is Henkin constant? Henkin constant is used in the proof of the completeness theorem for first-order classical logic. And in short, Henkin constant is a conditional witness for an existential formula. Yeah, it is somewhat looks similar to scoring variables in computer science, but the direction and the logical rule are certainly different. So in the Henkin construction, we repeatedly extend the series T by adjoining Henkin constant and Henkin axiom for each existential formula. And the idea here is not the theorem itself, but introduces a conditional witness for an existentials and use it to propagate facts. Okay, so let's see how our detection algorithm work in EGLOG. Suppose we are given with two constraints that jointly constitute an SOS1 constraint on even x's. So GIG modeling 1 first encodes each constraint as an EGLOG rule, possibly with premises. While doing this, it attaches nonces to each bound variables. And this makes the variable act like Henkin-like constant. Okay, so for upper bound constraint, we declare a rule saying that
saying that under the premise that I is less than n, this upper bound constraint holds, and we also register this particular unique constant I98 together with the fact that it fulfills this premise. And for upper bound, for this constraint, as this is not parameterized over any parameters, so it is just assertion that this sum is at most 1, and we also register nonce variable or Henkin constant for this bound variable I that fulfills I42 is less than n, and it is even. So then we register SOS1 detection algorithms rules and learn EGLOG. The first rule just declares just that for binary variables, the SOS1 and for binary variables, if its summation is at most 1, then it is SOS1. And the second one is just combines binary variable SOS1 and upper bound constraints and lower bounds, and to get general SOS1s. So then, so because the nonce carries the bound variables facts, EGLOG can connect the two constraints and derive the SOS1 structure over X. So the first SOS1 is derived just immediately from the first and this, and then it infers that X or xi42 always satisfies this upper bounds constraint, and therefore X is also SOS1, satisfies SOS1. Okay, so this worked for simple cases, but we also had to optimize the premises of the generated rules to have practical performance. For one model with the constraints on the right, this EGLOG did not terminate even after an hour. At first, we thought that the cause is the explosion in equality saturation, but it was not the case. After inspecting the trace log, it turned out that EGLOG did not even reach the equality saturation after an hour. And the issue was that a constraint premises had been encoded a single membership like this. Yeah, it's quite huge, and EGLOG got stuck on this. The fix was to apply the comprehension retriggering from the first part, and it gets like this. Yeah, it's now decomposed into several conditions and now human readable and really debuggable. And now EGLOG gets happy with it and terminates in less than 1 second. Okay. In summary, in our previous implementation, we achieved constraint detection modulo equivalence using EGG, but detecting multi-step constraints was cumbersome because it requires back and forth between EGG and log. But JGA modeling 2 solves this more declaratively using EGLOG's logic programming paradigm. And although EGLOG currently lacks proper handling of bound variables and substitutions, the Henkin constant-like trick lets us propagate information across bound variables. And the practical lesson is that we must simplify EGLOG rule premises, otherwise EGLOG may get stuck before reaching equality saturation. Okay. Now we move to the conclusion. Okay. JGA modeling 2 is a mathematical optimization modeler written as a Python ADSL and implemented in Rust. And we introduced 2 applications of EGLOG to mathematical optimization. And the first contribution is readable mathematical output for models using higher order functions. We formulated this as program transformation and optimization with retriggering into comprehension syntax and equality saturation rebuilding for rebinding optimization. And the second contribution is EGLOG-based declarative constraint detection using Henkin-like constants. And one important lesson is that gigantic premise can choke EGLOG before equality saturation. Okay, thank you for listening.
Okay, thank you. We have time for a few questions.
Hi, thanks for the talk. So you mentioned that things like beta reduction are not considered. So I would suspect it's relevant to hygienic macro, because in resugaring, if you have such binding, then the hygienic things matters. So is it the case? And if it's really about you don't need it, or it's about EGLOG cannot support the solution for hygienic macro?
Kind of it sounds useful to me. So currently we are just generating random numbers by hand in our side. So if EGROG provides us the hygienic variable generation, it should be useful to us. Yes.
Okay, let's thank the speaker one more time.
Thank you.
And with that, let's turn our attention to the last, but certainly not least, talk of the workshop. So please take it away when you're ready.
Yeah. Hi, hello. Yeah. Hi, hello everyone. My name is Brent. I'm a second-year PhD student at UIUC. I'm presenting the presiding framework for profile-guided numerical rewriting at full application scale. This is joint work done in collaboration with Weimar Sasia, Ivan Ivanov, Jan Hugelheim, Paul Hofland, and my advisor, William Moses. So it is always desirable to make a piece of numerical software faster and more accurate. However, optimizing practical numerical code is often challenging at 3 levels: context, scope, and skill. By the end of this talk, I hope to convince you that profiling and compiler optimization are the key to address all 3 challenges. So first of all, context is really important when doing numerical rewriting. In this simple code example where we accumulate a nonlinear operation to a running sum, in this example, if we were to lower the nonlinear operation to use float, that is also known as single precision floating point numbers, we get a 1.6x speedup with a relatively small error. That's 1 in minus 12. That's in general safe. But if we go further a step by lowering the running sum to using float, the error can bump to 1 in minus 4. That's often risky for an application. This is something that can be exposed using profiling within the compiler. By just running 10 iterations of this loop, we can find that the reduction here is 10kx more sensitive than the nonlinear operations to such kind of precision changes. We propose a structured critical value hypothesis. The values that's critical to accuracy of the entire program are often structural. For example, there are certain kinds of computation like reduction, cancellation, one-hot vector, thresholds, that's very structural, and even a small surrogate profile can reveal the key information needed to do numerical rewrites. And there's another challenge called scope. Precision is just one possible rewrite. There are also other kinds of rewrites that may be better for a piece of program. For example, in this expression, we add a big number to a small number minus another big number. If we were doing using FP32, we can get the +1 rounded away because we have only 23 mantissa bits, and we get a wrong result, 0. And one obvious fix is to invest more mantissa bits to it by using FP64, and the +1 will survive under this precision, and we hit a fundamental performance accuracy trade-off because we have to pay more runtime cost to using a higher precision like FP64. And there is a different class of rewrites called algebraic rewrites that can circumvent this trade-off, but doing this requires expertise, and for things to be correct, because you can do some like Taylor expansion that can be wrong for some inputs, and also require some program analysis for the rewrite to be profitable in terms of performance. And there's a third challenge called scale. For a practical application, for example, this simple foo function that's written in C, the mass can be hidden behind a bunch of complexity. For example, control flow. For example, there can be memory loads and stores. There can be function call boundaries that make a lot of existing source or binary level tools fail because they cannot see through these complexities. So our key insight here is that a production compiler has the exact necessary machinery to circumvent this challenge because there are standard LVM passes, for example, mem2reg, that converts the memory loads and store into an infinite register form. There we can also do some control flow graph simplification to eliminate some control flow branches to fold them into a select instruction that so we get a straight line program, and we can also do inlining to fold this foo function to its surrounding context. So in this example, if we do inlining, we know the caller wants this max expression by calling this foo function. So we hope to answer two key scientific questions here. Question number one, can we automate advanced numerical rewriting techniques, including algebraic rewrites, in compilers? And there's a second question, how much performance are we actually leaving on the table due to suboptimal choices of precision and expressions in the real application? We built Poseidon to answer these two questions, and Poseidon is the first framework that automates advanced numerical rewriting techniques within the production compiler. It operates as a two-phase compiler. In the first compilation, we instrument user program to collect the numerical context necessary to perform context-sensitive rewrites, like the reassociation we shown in an early example. And in the second compilation, we perform the full application scale numerical rewrites in the following stages. First, more details on the profiling path. We perform pre-optimizations that's actually standard LVM passes to expose underlying mass. So the compiler can see more context of the numerical program. And we generate runtime profile, including execution counts, running sum of values and gradients per floating point instruction. And we then do subgraph extraction to get expression graphs through a linear time flood-field scan of LVM intermediate representation of the application, and expression graphs are used to synthesize numerical rewrites. We synthesize these numerical rewrites in the candidate generation phase. We have multiple classes of rewrites. So class number 1, we can do algebraic rewrites by using external tools called Herbie. That's based on equality saturation, and we can also propose expression graph precision changes in this phase. And this phase is also fully extensible to a broader scope of rewrites. In particular, we invoke Herbie to generate floating point expression rewrites. We as a compiler can identify LVM expression graphs that's supported by Herbie to do rewrites, and we can use compiler optimization to make this subgraph larger by including more numerical context, so Herbie can perform more effective rewrites. Poseidon can also be the compiler substrate for other tools because within the compiler, we can see more numerical context. And in this example, the Poseidon can construct this Herbie input expression by injecting the profile bounds into the FP core expression as preconditions, and call Herbie to generate a bunch of expression rewrites. And then having a bunch of expression rewrites or precision changes candidates at hand, we want to evaluate the candidate rewrites performance accuracy impact on the entire large-scale application. We use two models, a performance cost model. For example, we perform micro benchmarking on LVM floating point instructions to assign them integer costs, and we sum up the affected instructions per instruction cost as a cost measure of the rewrite, and we can also evaluate their accuracy implication by sampling random inputs from the profile bounds and compute a local error using a high precision MPFR arbitrary precision float as a reference, and multiply with a profiled global sensitivity measure over affected instructions to get a global accuracy measure. And having a bunch of rewrite candidates evaluated in terms of cost and performance, we can use a DP solver to evaluate a Pareto frontier with a bunch of performance accuracy trade-off. As a result, for any given cost accuracy budget, Poseidon can have the best rewrite strategy according to the performance accuracy model. And we evaluate Poseidon on multiple large-scale applications. For example, here's a quaternion differentiator. The original program is the red triangular symbol on the lower right corner, and it's using floating point 64, and it's fairly accurate, and we can generate these blue dots as the rewrite as the optimized programs, composing rewrites in different ways. And this yellow star has a 1.46x speed up at a cost of a higher error, and we can also use a lot of accuracy improving Herbie rewrites to reduce the error by 27% by paying more compute time. And here's a particularly interesting result. We can apply Poseidon on a large DOE proxy application that's more than 5,000 lines of code with 200 loops. And the original program has 12 UOPs away from a highly accurate MPFR reference result. And Poseidon can automatically apply 9 algebraic rewrites. That's fairly complicated to achieve an optimal FP64 error with no substantial slowdown. And there are also existing ways to get more accurate results. For example, there is hardware accelerated FP80 that takes more than 6x more runtime, but still being 2 UOPs away from the ground truth. We can also use software emulated libraries. For example, we can use 74 mantissa bits floating points using MPFR, and the runtime is at least 500 times more than a native floating point. And we have an ongoing work of applying Poseidon to rewrite accelerator code. They're fully leveraging an arithmetic throughput of an accelerator is challenging for multiple reasons. First of all, most of the flops of an accelerator are in specialized hardware instructions, for example, a tensor core, and raising scalar operations into tensor core operations requires expert analysis. And there is a recent trend of deprioritizing high precision. For example, in new NVIDIA GPUs, FP64 runs at only 1/64th the rate of FP32, and the GPU has a very different cost model. Because of this, instead of using native FP64, it may be sometimes faster to emulate high precision arithmetic with lower precision floats, for example, FP16. And we want to answer this question here: can we automatically choose the right rewrite strategy for a practical accelerator code while still satisfying an application level accuracy target specified by the user? And we find that Poseidon's profile-guided optimization approach is an answer to this question. We extended the Poseidon's candidate generation phase with floating point emulation techniques. For example, for scalar operations, we can do multi-float by composing multiple scalar precision floating point numbers using lower precision numbers to emulate a higher precision, or we can do multiple lower precision matrix multiplications to emulate a higher precision matrix multiplication using Ozaki scheme. And we can also propose raising rewrites to raise scalar operation into tensor core operations, given a user-specified accuracy target that can differ across application and across scientific domains. Poseidon can solve for the right rewrite strategy. And we applied Poseidon to an astronomy application that's GPU accelerated. Herbie and multi-flow rewrites can make things 4.4x faster while still having a near FP64 accuracy. And we can also automatically raise an insensitive matrix product within an eigensolver to use TF32 tensor core operation that previously required expert analysis to understand which scalar operations are matmos and are less sensitive to such precision reduction. And we also applied Poseidon to a chemistry software. There is a scientifically meaningful threshold in literature for this application, and given this user-specified accuracy target to produce scientifically meaningful results, Poseidon can automatically raise some scalar operations to tensor core and materialize Ozaki scheme to improve to achieve a near FP64 accuracy while being 4.46x faster and about 2 times faster than a Kubla's dense general matrix multiplication. And this concludes my talk. I introduced Poseidon which is a profiling and compiler optimization approach to provide context, scope, and skill needed to perform numerical rewrites of large-scale applications. And we can do automated numerical rewrites at full application scale within the compiler. And recently, we extended Poseidon to enable fast and accurate accelerator code automatically within the compiler. Thank you.
Okay, thank you so much. We have time for a few questions.
I wonder if you've considered the alternative standard for approximate numerical representations called POSIT, standard POSIT 22, and if that compares to, if you've done any comparisons on that, I'd be curious.
We actually talked with the professor who proposed that, and POSIT numbers are very interesting and absolutely can be integrated to our candidate generation phase. We can propose rewrites to use POSIT numbers instead of the regular IEEE floats. That's a future direction we are happy to explore.
So I think from EGRAPHS rewrite point of view, there's kind of this interesting thing going on where inside Poseidon, you have this sequencing where you do LLVM-based rewrites, then you do rewrites suggested by Herbie, and then you do some kind of, you said, dynamic programming style extraction to pick the best speed accuracy trade-offs. And then, within Herbie itself, there's also an eGraph that's also sequencing a bunch of rewrites to propose the candidates. So I guess what I'm curious about is, it clearly seems to work, but is this just a pragmatic design, or is there something important going on here where the LLVM-based rewrites need to be sequenced before some of the Herbie-based ones? Is there some wisdom in this schedule where we've got different kinds of rewrites that apply at different times and multiple levels of extraction, or is this just a pragmatic convenience from Herbie was already available?
It is true that Herbie do have this kind of soft within it, and there are a lot of complexity in practical application to prevent us from just relying on a Herbie-style internal soft, because there can be multiple expression subgraphs scattered across the entire program that may have different kinds of sensitivity, that we need a global kind of Poseidon-style soft, at the end after Herbie's internal soft for each intermediate subgraphs.
Thank you.
Yeah.
So please correct me if I'm wrong, but for your profiling is guided by a first order approximation of floating point error, right?
Yeah.
So a problem with first order approximation of floating point error is the model. So another important part of floating point is overflows and underflows, and overflows and underflows, nans, stuff like that is out of model with your first order error approximation stuff. My favorite example is an expression square root of 1 plus x square, where if x is very large, in floating point this will overflow, but the actual the actual answer to square root of 1 plus x square is is representable in floating point. So do you care about errors like this? Is this something that you want to fix?
There are multiple ways to fix it. For overflow or underflow, this frequently happens, especially for accelerator code, because the range of supported floats can be really small. If it's only 16-bit of a float, we can assign a large constant as a penalty to that kind of overflow behavior. There are also a way to extend Poseidon's soft or profiling phase with the more advanced, or I should say, more faithful approximation instead of the linear approximation we applied here, that's totally doable in profiling phase.
Okay, let's thank the speaker one more time.
Thank you.
And that concludes our program. Thanks everyone for attending, and thank you to all the presenters. I think this was the best iteration of this workshop yet, and I'll see you all at the main conference. Yeah.